Hello, everyone. Welcome to the 19th edition of the International Conference on Network and Parallel Computing, NPC 2022. Due to the COVID situation this year, the meeting is held online virtually. First, we would like to thank all the committee members, from the various chairs to the local organizers and the reviewers. This year, a total of 89 submissions were received in response to our call for papers. These papers originated from Asia, Africa, Europe, and North America. Each submission was sent to at least 3 reviewers, with an average of 4 reviewers per submission and up to 5 reviewers. Each paper was judged according to its originality, innovation, readability, and of course, relevance to the expected audience. During the double-blind review process, we had the authors and the program committee members indicate any conflicts of interest and assign reviewers accordingly to avoid such conflicts. Based on the reviews received, 23 full papers and 8 short papers were selected to be published in the NPC 2022 proceedings, which makes the acceptance rate at 35%. Among these, 5 papers were further selected to be extended and submitted to a special issue of the International Journal of Parallel Programming. 5 main themes were identified during the conference, which you will hear today, which include computer architecture, deep learning, cloud computing, emerging applications, as well as storage and I/O. And the papers in this volume are grouped accordingly. We would especially like to recognize our 3 guest speakers, keynote speakers, who will give exciting presentations. Ms. Alcon from the United Nations, who would discuss how computing innovations and cross-sector partnerships would help the most vulnerable part of the world and would help reach the United Nations Sustainable Development Goals. Professor Dennis Tristrom from MIAI Grenoble Alps will explain sustainable resource managers for parallel and distributed systems. And Professor Yuhao Zhu from the University of Rochester will delve into the visual computing challenges for emerging applications such as AR, VR, and autonomous machine computing. We sincerely hope that you enjoy this year's NPC 2022. Now, let's start with the keynote speeches.
Dear NPC 2022 participants, organizing committee, I'm Alcon, Senior Program Advisor and Chief of Resource Mobilization Outreach and Strategic Communications at the United Nations Technology Bank for the least developed countries. Today, I'm very thankful for the opportunity to exchange some thoughts and ideas with you at your annual conference on how do computing innovations and cross-sector partnerships can help the most vulnerable to reach the UN Sustainable Development Goals. As this year's conference is taking place in an ancient city in China, in my mother tongue Chinese, we have a nickname for the hardworking computing and engineering professionals called Ma'neng, or in English, the digital brick builders. In fact, computing has become such fundamental bricks and mortar for today's society, the rich and the poor, for education and addressing climate change, from meeting basic needs to create a metaverse. All of these digital bricks and foundations that you're creating is not there to advance just for their own sake, but they're indispensable means to an end, that is, inclusive prosperity and sustainable development, with the UN and with its member states that all signed up for the 17 goals. Now, my first ask for you today is that all my fellow digital brick builders, when you are computing for solutions, do you have the end in mind? Have you mapped out who are the end users? And in what context are they using your products? are there synergies you can create through computing and with other service providers? I give you an example. Many years ago, I was in South Africa, leading the building of the biggest biocomputing center on the African continent for early sequencing of communicable diseases. At the beginning, it seems just like a pure computing issue. But soon, as we find out, there are way more aspects than that. For instance, data ownership. What are the research to solution designs? What about power supplies and sample transmissions of the biotech centers? All these needed cross-sector and cross-country collaboration to address one by one. This is not a unique case, which I just listed. Over the years, I have found out that engineers are also required to be the solution builders and the system thinkers through which their new innovations will come in. This is a tech, not a product case, which I would address it as technology is not a product, and the product is not a business, and the business is not a solution just by itself. All these links have to be worked out deliberately by you and me. And the way to start is to having the end in mind. Thinking, are my solutions holistic? Are they self-generated? And they feeding into the big ecosystem? So how do we make the solutions more holistic? I am a big advocate of cross-sector partnership and multidisciplinary thinking. And these came from my project experience in more than 100 countries and across technology, investment, and public sector, including a long history in the United Nations system, leading international development and innovation. Take, for example, my current organization, the UN Technology Bank for Least Developed Countries. It's a UN entity mandated by the General Assembly to enhance science, technology, and innovation for sustainable development in the world's 46 least developed countries. So who are the LDCs, the least developed countries? These are the countries that are facing severe structural impediments to growth and account for less than 2% of world's GDP. Now, through our needs assessment, you probably can imagine it's more than clear that meeting computing needs, even in these poor of the poor countries, is fundamental to their country's present and future. If we're missing that, we're missing a huge part of human rights. For instance, using computing power to read satellite images is crucial to help residents in the Sahara Desert to find water resources. Also, building digital medical records and train the engineers to understand and do so could help the Kingdom of Bhutan to advance its public health system. Even to finance climate and ecosystem protection bonds, you will need computing power to calculate the baseline and monitor the return on investment to be able to issue the bonds in the public and private markets. Therefore, in international development, we call our interventions as programs. So as you see, you and I are both programmers, and our efforts and vision will have to converge into one, which is to help all societies to reach their potential and sustainable development goals. Now, you may ask me, what are the best ways the public and private sectors can collaborate? And how do policymakers and engineers fill in each other's gaps? I will give you an example from my recent experience as a leader and judge for MIT Solve Social Impact-Driven Technology Annual Challenge, which you can Google and find on MIT's website. I was very impressed to review more than 50 cases and select the finalists to present to the panel. By their experience and cases, that how engineers have brought computing into solving specific challenges. For instance, an app that matches refugees to live translators when they need to interact with humanitarian workers. And, for instance, Doctors Without Borders coming from foreign countries to address language barriers. And another example is that fintech solution that would enable the traditional mom and pop small shops to receive their payment through users' cell phone bills, which are much easier for the residents in the small countries or these developed countries to have access to. These are just some few examples on how computing is there to help the most vulnerable and those who usually leave behind to meet their needs. I believe with your brilliant mind, once you start also looking for those gaps, those unmet needs, and underserved population, you will always be able to design a computing solution to it. Therefore, today, by appearing as a speaker at your annual conference, it's my first attempt to call your attention into regarding computing as a brick builder, a digital brick builder, a human rights brick builder of the inclusive, prosperous human future. And I'm here with the whole UN family to collaborate with you. This is my invitation and my warm welcome to all the engineers and IT professionals to join hands with the public sector, with the United Nations, with the policymakers, with civil society to build inclusive solutions for everyone by starting with the ends in mind. Thank you.
Hello, everybody. So I would like first to thank the organizers of NPC to give me the opportunity to present a hot topic today. Let me first share my screen. Here it is. Okay, so this subject is sustainability in HPC systems. First, let's start by a picture. So we know that digital computing now is everywhere, and this is increasing. Okay, you have a lot of IoTs, for instance, and this is visible, but you have also a big part that is completely hidden. Let's consider, for instance, this big warehouse where there are a lot of smart algorithms that are running everywhere just for distributing all the items to everyone all over the world. But besides these small devices, somehow, you have at the other side of the spectrum, big machines. So you know all, obviously, the top 500 of the largest machine all over the world. And last June, it turned that we just get the step of exaflops on a real benchmark. And this machine is called Frontier. It has more than 8 million of cores with different cores, with accelerators, and a power efficiency of 52 gigaflops per watt. If you see the picture of the top 500, Frontier is at the right side here, at the middle of this is the picture is in red. And you have the sum of all the machines just on the top of this point. And you will see here, you see here the evolution of the top 500. Okay, in green below, you have the smallest machines. So there is a big gap between the rank 500 and the first rank. But if you look at this more carefully, I just do some stats over the 10 last years, and it appeared that the performance in terms of flops has been multiplied by 32, a factor of 32, while here the average of the top 500 has been only multiplied by about 20. And if you are looking also of the top green, that shows the best machines according not to pure performance, but to efficiency, power efficiency. In the same period of 10 years, it has been multiplied by 14 for the highest one, while in average, all the machines have been multiplied by 18 only. This shows simply that performance is increasing a lot at an exponential rate, while the efficiency is also increasing, but at a smaller rate. It's like here we are running here to something, to performance only, but there is a storm here because somehow there are bad events that may come. For instance, here you can see a guy who is behaving completely like before, but in a situation, crisis situation. Okay, this is somehow a joke, but it reflects somehow the main question: could we really behave like before? I would like to address this. What's the link with HPC? You can say, okay, is the rest of this performance is based on high-tech evolution, but it's not for free. It has a big impact of the environment. If we focus on the CO2 emissions, okay, I would like first to show you how to measure all this and to really understand the hidden part of computing that is not only computing by itself. Then I will present some directions that mitigates the global warming in the field of resource management through a project that we have developed in Grenoble, and I will open discussions for further challenges at the end. This talk is divided into two parts. First part is about energy consumption challenge, and I will explain somehow the basic of this. And then I will turn to the topic of resource management. Okay, first part. Let us start by some curve here that shows the clear anthropic origin of this warming. You can see here a chart coming from the Industrial Revolution. We put the zero here at the middle of this period. And you can see here a big acceleration. And this is here the synthesis of 4 different databases. So they all converge to a warming that is already 1.20 something degree. And actually, this is not the first part that we face this warming in the world. Yes, for sure. But here, what is very new is this big acceleration in a so short time. We had this such acceleration, but over 10,000 years, so it was very, very long time. This is not a good news. Now let's go to some warming projection based on some analysis. I took this from Climate Action Tracker site, and the historical data on the left here are those who are that are measured, and then you have some scenarios, and you see that all scenarios will see a decreasing here in the somehow because we take some decisions to face the problem, but in the worst case, you can see that we will lead to some warming that are very, very high, and even the best scenarios here are still going to some significant warming. Okay, now how does it work? I take something out of the pure computing field. What about greenhouse gas? So you know that there exists naturally, fortunately, because otherwise you cannot have life on the Earth. Simply, it will be too cold. And but there's a big balance, a perfect balance of this that allows the temperature on Earth to be okay for life. And we know these gases. There are several, but there are 7 main gases. We know well H2O and CO2, but now also CH4, N2O, and ozone O3. And we'll focus here just on CO2, but it could have been the same on different examples here. The problem of CO2 is that it remains in the atmosphere for a very long time. So as soon as we emit something today, it stays for 1 century at least. Now, what about energy? A human, expends about 2,000 to 5,000 calories a day. This, if you want to transform this into some mechanical energy, like for cars or whatever, then it corresponds to about maximum of 500 watt per hour. And we take always the same unit, that is kilowatt per hour. okay, it is the energy corresponding to any electrical equipment that runs for 1 hour at 1000 watt. For instance, 1 liter of oil corresponds roughly to 10 of this unit, 10 kilowatt per hour. And the energy comes from a mix. It comes from oil here, from coal, and from wind, or from nuclear plants, okay? And any human activities require energy. And we need a lot of this with our modern lives. If you see the repartition in France, okay, it's a bit special because we are, as you see in the chart, we are using mainly oil. This is because of the transportation and cars, a bit of coal and some gas, and a big part of electricity that mainly comes from nuclear plants. Okay, this was a rather old source, but the proportion remained about the same. If you see this repartition all over the world, you see this is completely different. The main is coal, and then oil and gas, and all the others. And you have nuclear is very small, and all renewable energy are very weak also. You can see here in this chart 2 interesting situations that during COVID pandemic, and on the top right, you have a kind of small decrease of the global energy. Okay, that is a good news from the warming. And you can see also what is the total amount here of the consumption in CO2 emissions in 1 year, about 35 to 40 billions of tons of CO2. That is a lot. Now, just look at some pictures here about increasing of population, increasing of use of water, of whatever you like, any human activity. We see that there is a big acceleration from 1950. And this is the origin of what we call Anthropocene, the new era where the activity of humans takes the lead over all the other activities. And you can see here the same kind of exponential acceleration. Now, what about coming back to the digital sector? Here is the repartition coming from our World in Data setting. You can see all domains here and all the energy spent here in term of emissions of CO2 and greenhouse gases. But you don't see any digital here. Why? Because digitally is everywhere, even in agriculture, even, okay. And then you cannot see in this chart exactly what is the part of the digital here. So what is the part of this digital? So if you see, there is some part about production or use of personal computers, networks, data centers, and into personal computers you put or even smartphones. And for data centers or HPC platform, this is our topic today, the consumption, the proportion between production and use is about 50 to 60% as far as we measured. And this is somehow, these numbers are very hard to get, but actually this is something that we know while we are speaking with our industrial partners. Now, the impact here of CO2 emission in terms of global consumed energy is about 5 to 6%. Okay, it corresponds to a bit less than 4% of the CO2 emission. That is a lot, actually. But what the main problem here is the growth of this annual growth is from 6 to 9. So this is very big. And now here we know that we should reduce this. We should reduce to mitigate global warming. But this sector here is in expansion. In France, it corresponds to something that is almost double from the civil aviation sector. And it is completely hidden again of any chart. Here comes a nice curve that shows somehow last year the scenario of business as usual, doing like it is, it will still grow at a rate of 9%. But there are different scenarios here that are even worse. So we are really to take care. I will come back to this chart just after. Now, I will present two things here that are very important to understand how does it work and what could be our measure in order to put some leverage mechanism to mitigate the CO2 emission. There are LCA, life cycle analysis, and rebound effects. So let's start by LCA. LCA, for any production of digital component here, we start by extracting something, and for extracting for mines, for big mines here, and it costs a lot of CO2 emission also, obviously. After this, we have the fabrication of the component in some big companies, and then transportation. Obviously, there are some transportation also from mine to the fabrication, but okay, I will isolate this step separately. And at some point, then there is the data center, the new HPC system that is deployed, and you can run here. This is an example of a run of a weather forecast, for instance. And then, as after 4-5 years, all the computers become a bit old, and then we may or not use them for another topic or refresh them, or we can have the end of life of this component. This is the whole steps of the life cycle analysis here. And you see that usage here is only at the bottom, is only a part of this whole system. What now is rebound effect? Rebound effect here is, let's consider, this is a kind of abstract presentation, but I think you will get it. Let's consider any material resource that could be CPU, it could be energy, whatever, okay? And imagine a set of users that are using this energy, and they are consuming the whole resource, okay, at some point. And now comes a kind of technical improvement. And within this technical improvement, people are able to do the same, but in a much, much smaller use of the same energy. So here, in my picture, you see that there are some idle resources here. If we stay as we were before the technical improvement. But this idle, what to do with this idle stuff? We could save it completely to mitigate climate, or the same users can be a bit more, can do a bit more. This is always what we remarked. Okay, we are asking more because there are some available resources. We are using more, and at some point, if we are using more and again, there is what we call the backfire. This is the moment where the new technology that is deployed allows much more people to use this resource as before. And the global thing is that at the end, you will use more resources than before the improvement. This is what we call Jevons effect or rebound effect with the phenomenon of backfire. And there is something even worse, that all these resources that are freed, that are idle, could be used by something else because they are available somehow. And this is what we call an indirect effect, second order rebound effect. Okay. Now, what is the problem with life cycle analysis? Because people usually did not go to these measurements. Why? Because it's very difficult. First, there is limited available of stats, and the data are not public. They are usually with the admin of the HPC system, and they don't want to be shared. And all the life cycle analysis are biased because if we ask our colleagues in company of constructors, they are far too optimistic actually. And okay, another fact also that makes it very difficult to estimate is that it takes time to establish a full life cycle analysis. We try to do this in my group for several components, but it's a very long time. It needs 1, 2 years or more. And if you are comparing this to the lifespan of the machines, of the smartphones, for instance, this is too long, and to provide the data, and the digital component are already in the next generation. Another problem is the systemic effect that is very complex, and so on. What's the takeaway message of this presentation of LCA and rebound effect? That most climate impact analysis, that there are some, but they are only restricted to usage phase of the LCA and not to the whole effect that should be done. Coming back to HPC now and Frontier, if you're looking for Frontier, Frontier has been deployed in Tennessee, so it's used in Tennessee. Tennessee is on a good year. You have the mix, the energy mix of the US. You guess that this is the US map. And actually, the darker is the more carbon intensive it is. So here, Tennessee is not a so bad state for this point of view. And actually, here, if you see exactly the distribution on Tennessee Valley here, these are the data that are available. I just look at some adequate website in the US, and you can see here that there are a lot of nuclear plants here. You have a bit of coal, a bit more gas, and all to all, and renewable is only 3%. So it's a reasonable one. It does not use a too bad energy, too carbon intense energy, but it requires 52 gigaflops per watt. Okay, and it consumes 21 megawatt. This corresponds roughly to one round trip Paris-New York per hour. This is a lot, just for usage of this machine. And again, no data about the phases out of the usage are provided here, and no news also about rebound effect. It's like you have the full LCA here, and that all these phases are completely forgotten here, and you just focus on a small part of the life cycle analysis here. And for this part, then we can have some information and try to improve this part. But all parts should be also improved. Okay, now a second takeaway message here is that we behave as scientists like the energy is completely cheap and infinite. But this is no more true. What we really have to face is think about our algorithms into a term of finite resources. Now, let me add another curve into the previous chart. This is the curve here below from 2019. Here, it's what we should do is to keep a trajectory that is the same as before. We had a big improvements here in our systems. We should be able to behave within these finite resources, at least not to increase the use of the energy for running our algorithms. Okay, this is the last slide of my presentation. I will now turn to the more specific topic on resource management. Hello, I'm back for the second part of this keynote. So here it is. Now let's go to sustainable tools. So as we recalled in the first part, parallel and distributed systems are more and more complex. And the characteristics are, there is a continuum between mobile devices and edge computing, cloud computing, and HPC platforms. And they are composed of several heterogeneous components with accelerators and several levels of hierarchy. They are also targeting large and extreme scale, as we saw with Frontier. And consequently, there are some reliability issues because of the large scale, large number of processors. And we also have to deal with a lot of uncertainties everywhere. Moreover, all these platforms consume a lot of energy. Let's recall how does it work when I submit a job to a platform. Let's say this is the first job on, let's say, dynamic molecular dynamic code, and then at some point, just after, there is a weather forecast run, and then speech recognition, and so on. All these applications that are submitted compete to the same resources. Here is on the left HPC platform. And symbolically, we have a queue of jobs. Each job J has some characteristic of required number of resources. It could be heterogeneous resources with accelerators. And they are submitted at some point called RJ. R is release time of job J. And the users provided usually processing time. This is an expectation of the running time of the job that is overestimated because usually the rule, this is what we call the wall time, and the rule is when we go over this time, then the job is killed. So usually, obviously, we have to overestimate the processing time of the job. These are the characteristics of the jobs that are submitted to a platform. Here is a run of what, so I just did a run on our machine here, a small machine, part of the machine with 128 processors over 3 hours. As you can see, there is a kind of warm up at the beginning, a startup time with few jobs, and then there are full utilization. These are some standard algorithms that are used here with our visualization tool. Now, what's the definition of the resource management? You know this very well. I will go very fast. This is somehow answering to 2 questions that are where and when. Where to allocate the jobs and when to start the execution of these jobs that are allocated at some processor. And there is also the question of how to deploy all the jobs everywhere, so with their data. And there are several objectives that should be optimized. We can simply go through throughput, trying to have the maximum throughput as possible. We can minimize the average waiting time of the jobs. That is a kind of fair objective, or targeting a full utilization of the platform, and so on. All these objectives are oriented toward performance. There are a lot of theoretical studies on this. So when you want to Google scheduling and parallel systems or batch scheduling or whatever, you have thousands of papers. So people look at this problem like stream packing problem. We can also derive some approximation bounds of algorithm in order to be not so far from the optimal. But usually, all these theoretical studies are done on ideal models that, for instance, have no communications and are far from reality. And somehow, they are mostly targeting offline setting where, okay, you can have a batch of jobs where you know all, but usually this is an online problem. And this is usually we run this algorithm by exact wall time, but we don't have too many studies that try to evaluate what happens when the wall time is less in practice, and so on. So usually, most of the scheduling policies are always running the same. In this submitted jobs queue, there are some priority lists, and you change the priority of the jobs. It can be explicit or not, or part of the policy to establish this priority. Okay, all is how to determine the best priority as possible. For instance, first come, first serve is a kind of policy. That means you just avoid starvation by taking the jobs in order of their arrival, and then you are mitigate this and improving this by some backfilling algorithms, and you can add other plugins that target different sub-objectives. And usually, when we propose new strategies, it's very hard because system administrators, they don't really like to have sophisticated strategy simply because they don't really understand all what is behind, and that this is hard for them to deploy something that they don't completely master. And another thing to tell about existing scheduling policies is that there are a lot of extensions, for instance, to multiple jobs. That means the number of processors that are required for running a job is not fixed at the very beginning. You have also some part that could be accelerated and so on. So there are a lot of sub-policy that could be also deployed within this framework of priority list. Now, if I take an example here, we run a paper with few of my students, and we compare some other policies like SPF. SPF is the minimum of processing time of the jobs, of the whole time of the jobs, or another policy that is good also, SAF, meaning smallest area first. You just take in the priority list the product between number of resources in the Gantt chart and the processing time, whole time, and we use the minimum of this in the queue, and they behave very well, much better than FCFS. But they have some starvation maybe, so a way to avoid starvation is simply to add a threshold to each job. As soon as you reach this threshold of the job, then you can execute it and putting another dynamic priority to this job in order to execute it. And the challenge here of designing a scaling algorithm is that we have to run low-cost algorithm. We don't need very sophisticated algorithm like LP algorithms, or if possible, we could also try to establish some worst-case bound guarantees for the scheduling policies. Is it possible on under some conditions? And we would like also to have the view of the users, a kind of fairness and the utility of the jobs, but also administrators of the jobs have also their own view of the problem. And usually they are not really the same as the users. So we have somehow to develop some multi-objective policies. And multi-objective policies maybe also may reflect performance versus reliability or energy consumption. For instance, they are antagonistic. When you want to minimize the energy, usually this is at the price of decreasing the performance, worsening the performances. We can also use on the new tools, online monitoring tools. I mean, they are low cost for just being possible to have interactive management. And we should also guarantee somehow that it's robust to some uncertainties, because again, there are a lot of uncertainties in these policies. Now, I would like to open a discussion about learning. So we know that learning may help because we have a lot of data. So we, I mean, 7 years ago, we published a first paper. There was only few at this time, where we use machine learning for improving the job allocations. And our aim was to predict some parameters of the problem, like wall time of the jobs. Okay, but we face several problems. Almost half of the jobs of the platforms that we use at this moment did not contain this information. So, and for instance, Zafir and Faitelson proposed a very simple policy without any learning. Just take the average of 2 last runs of the same users. So we succeeded to improve a bit this policy and to while targeting the average bounded slowdown on the different traces at this time, but we did not remark at the very beginning that this was as a price of worsening the maximum of the bounded slowdown. So what you gain over one objective, you lose over the other. That was not very good. And another observation of this study is that our policy behaves very well when the whole time corresponds to the actual time. But if it differs from this, then we get very, very bad performances, even if we had some dynamic adjustment policies. So then we turn to another idea that was to learn about the priority itself of the order of the jobs of the list. And then we succeeded here to have much better performances. So this is what I advise now. Instead of targeting to the parameters of the jobs that are hard to get and not so easy to use, just target the right priority of the jobs. And dynamically, you can change this priority and you can use machine learning for managing this priority. Now, if we target energy consumption, what are the possibilities to improve our resource manager? We can use speed scaling. That means adjusting the speed or the frequency of the various processors. Okay. You can also say that while the processors are still in use, even if they don't compute, when they are not shut down, they still consume some energy. So what we can have is a kind of hibernation or partial shutdown of the nodes in order to limit the energy used by some processors that are not computing. But here we can use also some specific hardware for accelerating some parts of the execution of the jobs. And for instance, when you target deep learning algorithms or whatever, very often a single precision is often to get the same performances. You can also develop some dedicated scheduling policies with energy budget taken as an input of the scheduling. You can cap the power, and you can also do a lot of things. And I will finish this list by, you can also develop some incentive mechanism with the users in order to have some help from them that could help to have a better positioning and allocation of their job. Now let's go through 5 minutes to our project called Energumen. Energumen was a project of 4 years founded by the French Agency of Research. And the objective of this project was to target the design of efficient methods for energy optimization here. And the idea was twofold. We tried to do some adaptivity in time, that's called elasticity. These techniques come from cloud computing, for instance, but we could also use adaptivity in space, in the resources themselves, and get a kind of malleability in computing or resource or memory resources. That means able to redistribute the number of nodes allocated to a given processor, but this is obviously at the price of some redistributing algorithm, and we should have the software stack that allows this redistribution, obviously. And another feature of Energumen was to use some data analytics for predicting job energy profiles. And as soon as we have a profile of energy, our idea was that it would be more easy to take into account these profiles to optimize the energy. So there are a lot of papers, so I just stress few papers there, but there are now more literature. These are rather old papers now. Okay, in the picture here, if you take the view of the perspective of the administrator of the machines, enargument is three items. First, an item of job energy profiles. Okay, we are collecting the data from last runs of the same users on the same machine. Then we are doing some analytics on this data in order to extract this profile. I will show you how that it works in a moment. Then we have the job allocation phase that is again done by some priority list algorithms, including whatever leverage mechanism that is concerned. So you can use one or the other in this priority list. We try to use several ones. And we also develop BATSIM, that is a software for simulating all the execution. And then were able to try different leveling mechanism and to compare them by replaying always the same different policies on the same data. And obviously, we have all the software for deploying this onto a real machine. And we use this on several machines that are available specifically in Grenoble. And now, the user perspective is not exactly the same as this one. As the energy, the user perspective is not really interested in any profiling of he or her job, and the user perspective is very different from this. So here I took admin perspective. Now, what about the energy profile? This is the first box here that I just described. The idea is to provide prediction of the energy consumption for the submitted jobs and to use later on the scheduling. And now this is based on some clustering or characterization of the profiles here. And we would like to learn the class of the new submitted job here and to try to cluster it with some existing classes. While here, the idea is to use some monitoring tools here. If we use monitoring tools for collecting energy here, what are the advantages here? We should have some low measuring overhead, otherwise it costs a lot and it has to be included into the LCA of the whole process. And also, we use more softwares because otherwise we have to use some watt meters, for instance, and to put on the series of multi-cores. And it costs much more in terms of carbon footprint. So we use more software measurement tools. And the drawback of this is that the energy value that we get are only estimations, and the absolute value here may vary a lot. We compare with actually real physical watt meters, and there is a bit different, 10 to 15%. Obviously, we also don't cover the energy consumption of the whole computing node with storage, with all the cooling mechanism. So this is also a drawback. We have to correct all these measures by some factors in order to have a better, more realistic estimates. And for this, we develop our own tool that is called Colmet. And Colmet is based on some tools that we are developing on Grenoble. But there are others. And in the frame of a European project called Regal, we are comparing Colmet with EAR, a tool coming from our Spanish colleagues, or BDPO coming from the company Atos also. I show you one use case here. Use case is on a big grid 5,000 large-scale public test bed, and this is one machine of this setting. It is in Grenoble. It has 1,024 physical processors. Okay, this is the detail here. And here are the two that we are provided here. So in a socket of 32 processors here, you can see the jobs with their numbering here. Okay, and you have the power profile just at the bottom of this figure here. Okay, a remark here: how much we could measure? What's the precision? we use here on the top, you have the every 5 seconds one measure, and below you have 1 minute. And you see here that it's not necessary to have a too precise setting, because you get the profile, quite very good profile, just with 1 measure every minute. You don't need 5 seconds. This is based on a REPL Intel library. This is also somehow limited carbon footprint of this, because we are doing less measures. And now the idea is how to combine this data here and the profiles with the policy of batch scheduling. Here, the idea is to use now another type of information about the use of the platform itself. For instance, at the middle of the night, usually there are much less jobs that are submitted on the weekend or holidays. So then the idea is to go through the users and to try to convince them to submit something at the middle of the night, and to get them to provide some reward and some kind of profit for next use. And the idea is to match this profile as much as we can. If we want to share 2 nodes on the same, 2 jobs on the same node, we are using intensively energetic job with another that is less energetic, for instance. But we have more different policies here. I don't want to detail too much. Here are some jobs, profiles of the jobs. So there are real jobs that are running on our machine here. We did this over 3 or 4 months of runs, and we get these profiles. You can see they are quite different. Some are very periodic ones, some are very different, or okay. And here, the trick here is to classify these jobs in regard to periodicity, to intensity, average use, maximum use, and so on. Okay, now I would like to open the discussion of job-centric here. What should be the part of the management system in this process here? Because the scheduler itself and the admin have more efficiency than the user themselves. And the user, they usually just want to use the machine, but they are part of this, and they can provide a lot of very useful informations to improve the whole system. And what's the methodology that we propose here is that we enrich the scheduler with some information here to take better decisions here. And in particular here, we are using some reward for encouraging people to give better predictions here. As soon as you follow recommendation of the system, then your reward is increased. Or we also developed some incentive algorithms that are less heavy than the reward. But this is the same. The idea is, again, to be able to get more information from the users, and that the users do not really wish target too precise objectives. We want to relax a bit their performance here. So here is an interesting tool that we are using also in Energumen. We are also targeting a good energy mix in order to limit the carbon footprint. Here is the picture coming from RTE in France. This is something that is available for the state. And you have the whole consumption of the energy of the whole infrastructure in France. And you have a curve of the prediction here in white. And at some point here, this was 11:15 here, every 20 minutes here, you have a new measure. And you can see here maximum of the consumption or minimum of the consumption. And you can even have more data here. I will show you another picture from RTE here. And then you can have at this moment exactly the position of the energy mix. And if here you have too much fuel or too much gas or too much coal that are fossil energy, then you can cap all energy of your cluster at some point. And when it becomes again better from the mix, then you can get more energy for your cluster. So the idea here is to be able to compute the best. Here, this chart show you here that is good because this is 60% of nuclear in this mix. So this was here a good situation where we can go up to the almost up to the max. Okay. So now what are the lessons learned from this project? I did not talk about rebound effects here because they are very hard to predict. Here we don't really know, and we did not provide any how to say improvement in terms of technology. But here we put a lot of effort to reducing the energy consumption. We succeeded in some to some extent here, but is it enough? Okay, here I don't know. The reduction was significant, but facing the big climate challenge, it's probably not enough here. And it was at the price of developing some digital functionalities here that are put in Slurm or in our own managing system OAR. And this should be also taken in the full LCA, life cycle analysis here, because it has a cost in terms of emission also. And here, obviously, when we are developing some new digital facilities, that means the admin or even the users are losing a bit of their control of their own jobs or of the whole tool. And this is not good. What we have to do also is to think, while developing new features, to be able to explain all what we are doing and to provide some way that people could really understand what happens. This is very important as a message learned about this project. Now the takeaway message, and I'm going to the end of my talk here, is I showed some that it's possible here to improve for better use in terms of energy. But the users should be aware of the cost, okay, and they should then participate, and maybe it's better for collaboration with the admin. And another thing here is that very few applications really need large-scale platforms. So what we could do here is to use our machines here. DAU is an old machine in Grenoble. It has it has been deployed 7 years ago. So the hardware is not new, but it's still very useful for all the machines. We don't really need new material here. So we're far from the top 500 in this extent. And obviously, don't forget, the best is always to compute less and to compute only if needed. You really have to provide while you are running some jobs if it's useful to use so many computing in regard to what you are targeting. Okay, and this is my last slide here. I take again the chart of the beginning here, and I really would like we urge to follow this what I call sobriety curve here. Let's try to do with the energy we have right now, and don't use too many new applications here, and try to keep your material as long as you can. Okay, so here is the end of my talk. So I would love to discuss with you. Don't hesitate to contact me. Maybe you can put in a subject in NPC, and then I will obviously be happy to react and to start communicating with you and to give more pointers and more insight of what we are doing here. Thank you for attention.
Thanks for the introduction, and thank you all for tuning in. I'd like to start my talk by introducing you to my first ever phone, which is this classic Nokia 3310. And I've had lots of fond memories on this phone, and one of the things I've spent a lot of time on is this Snake game. And that was how we played Snake back in 2000. Fast forward 2 decades, and this is how we play Snake today. We've got realistic 3D rendering, physics engine, stereo acoustics, and we can even use the phone as a joystick to control the game. The point is that mobile devices have become more capable, much more capable over the generations. Mobile system designers are able to push more performance into the devices, but the flip side of the story is that the energy consumption has also skyrocketed. This is a figure that shows the correlation between the battery capacity and the screen size. We sort of use the screen size as a proxy for the battery size. And you can see that there is a linear relationship. And the reason is that the battery density isn't improving, and so the only way of improving the energy capacity is to increase the battery size. And that's why we've gone from smartphones to phablets to tablets. And if this trend continues, we're going to be in the very near future holding these giant beasts next to our ears just to be able to talk to our friends. Well, I don't know about you, but I reject that future. I think that the future is actually going the other way, where devices are becoming smaller and smaller. For instance, this augmented reality device. Think of how small a battery it can accommodate. But at the same time, these AR devices are supposed to be doing much more than what your smartphones are doing. They are supposed to be always on, continuously sensing the environment, running AI algorithms, and providing you with intelligent services. And when I say AR, I don't just mean this particular device. AR actually represents a range of different emerging computing platforms like drones and autonomous machines and VR that what I call visual computing systems. These systems have to simultaneously do the following three things. They have to acquire massive visual data spatially and temporally. They have to interpret visual data that are acquired to provide intelligent services. And for some devices, they have to generate visual data for immersive consumption. So if you look at this simple AR application, the lenses, the optics and the sensor acquire visual data from the scene and generate images, and those images are then taken by the processor, which runs some AI and computer vision algorithms to estimate the pose or the orientation of the table, essentially an interpretation process, so that we can then draw the virtual chessboard and overlay that on top of the table. And all these information are then sent to the display, which then show the information and generate the visual data back to the users. And so this is an application that exercises all three tasks, all components. And it's a classic example of visual computing systems. And I'm using AR as sort of the running example in this talk, but hopefully some, if not all, the lessons and principles can be applied to other visual computing systems in the future as well. Now you might be wondering, so what I show on the left is the wild Pokemon Go game, which I'm sure a lot of you still remember, and that was a real AR application running on commodity mobile devices like a smartphone without requiring any special hardware, right? So that was a huge success by all accounts. And so the question is, going from what we know how to build today on the left to what we sort of envision in the future, is it going to be just a natural evolution of technologies, or it's going to take some sort of revolution? In this talk, I'm going to make a revolution case. And to understand that, let's take a look at how we're doing research today. It's fair to say that the vast majority of research efforts in computer architecture, which is sort of my area, are focused on interpretation, are focused on improving the processors. And we have been taking what's called a vertically integrated cross-layer approach, where we co-design the programming systems, the compiler, the runtime system, as well as the hardware accelerators, and sometimes even incorporating new technologies at the device level, right? So we take this vertical approach, and it has served us incredibly well, and it's evident from all the frameworks and tools and products that we are all using. And so I think there's no doubt that this vertically integrated approach is going to continue to be very important in the future. But if you look at the end-to-end system, the processor is just one component. There are many other components like the optics and sensors and so on. So what we have been doing, though, is to super, hyper, and uber optimize just the processors, try to improve its performance, reduce its energy consumption, sometimes even ignoring the rest of the system and just focus on optimizing the processor itself. And I argue that that's a mindset and methodology that's been taken by other system components as well. So sensor people focus on improving the signal-to-noise ratio and dynamic range of their sensors, Optics people focus on reducing aberration, improving field of view, and display people try to increase the color gamut of the displays and retaining the color reproduction accuracy. So I'd say that if I were to summarize the system design methodology today, it is designing and optimizing subsystems like optics and sensors and processors in isolation and then stitch them together. Well, I think that approach is not going to work going forward because it's really an integrated system where these different components have to work together for the ultimate goal, which is to provide immersive, intelligent user services, right? And so I would argue that the central tenet going forward has to be blurring the boundaries again. Just like how we have been blurring the boundaries across the vertical layers in the computing stack, we have to blur the boundaries again this time, but horizontally across different components. And the way I like to think about it is that at the end of the day, what we need to do is to architect different hardware components, whether they are optics or sensors or processor, but we have to architect the entire system to acquire, interpret, and generate visual data for users. And this would require us to rethink the abstractions and interfaces across these different subsystems. And this talk is going to be a whirlwind of promising and exciting, or at least to me, research directions in this horizontal paradigm. So the first thing I'll talk about is what I call perception-guided sensing and processing. Essentially, we're going to optimize and design the image sensors and processors guided by user visual perception, which is arguably what matters in the end because we're providing services to users and we're providing things that users can see. So AR/VR devices, they provide wide field of view, and that's arguably what enables immersive user experiences. But providing wide field of view also introduces more processing cost. So if you hold your phone at arm's length to your eyes, and your field of view when you're focused on, when you're looking at the phone, your field of view is about 25 degree, and that's a modest field of view. But any AR/VR device, any reasonable AR/VR device has to provide a field of view of at least 160, and that requires rendering, processing, generating one order of magnitude more pixels, and that's where the processing overhead is coming from. Well, the problem here though is that your peripheral visual acuity is actually very low. So on your retina, there's only a very small area that's at the center of the retina where the eccentricity is 0. Only in that fovea region, your visual acuity is high because that's where the vast majority of the photoreceptor, the cone cells, are concentrated. So as soon as you go beyond 10 degree outside of the fovea, your visual acuity becomes very low. What this means is that even though these devices have to provide things like 160 degree field of view, but at the end of the day, what you can really perceive in high fidelity is just the center 10 to 20 degree in the fovea region. And that gave rise to the notion of gaze contingent or foveated rendering, where you only have to render, if you can track users' eyes, you only have to render what is currently being viewed by user in the fovea region in high resolution. And the peripheral can be generated, not only rendering, but also the online processing can be done with a low fidelity. And the idea has been applied to not only VR, but also AR. So this is an example where foveated ray tracing is applied to AR devices, where the idea of foveated rendering allows you to trace, well, to save a lot of rays that you have to be traced, and that allows you to greatly improve the performance, the rendering latency as well. And people use foveated rendering not only to improve performance, but also to reduce the data transmission overhead. This is a paper from Meta, I think, where they show that in the cloud, on the server, you render in this foveated way, where the peripheral is very sparsely sampled, and that allows you to reduce the data transmission volume. On the client's device, on the VR device, you reconstruct the original, the full resolution scene. Now, the peripheral reconstruction quality is going to be relatively low because you've got very sparse samples there to begin with, but hopefully that's okay because your visual acuity there is low anyways. And we've recently done some work in this area where we exploit the peripheral color confusion to reduce the display power consumption. The idea is that in your peripheral vision, a lot of colors look very similar to you. So on the figure on the right, we're showing you a bunch of ellipsoids in essentially all the colors, or in the linearized RGB color space, I should say. All the colors within the same ellipsoid are essentially perceptually the same to you, so you can't really tell the difference between them. Now, why is that important or interesting? Well, it turns out that the display power, especially OLEDs, their power consumption is very much dictated by the color. So what I'm showing you here is a real power measurement setup where we cycle through different colors and measure the power consumption. And as you can see, white consumes the highest power because that requires all 3 subpixels to emit lights. And if it's completely dark, well, then no subpixel is emitting lights and the power consumption is the lowest, and other colors are in between. So it turns out that we can generate or construct power models that relate power consumption to color, and we can also construct perceptual models that allow us to predict the shapes of the ellipsoids. Now, with these two models, they can be used to guide the rendering process in such a way that minimizes the power consumption without affecting user perceptual visual perceptual quality. The geometric intuition is that for every color or every pixel color, we're essentially finding an alternative color, moving it so that it's still within the corresponding ellipsoid, but minimizes the total power consumption. So this is an example of perceptual guided rendering that minimizes optimizes for power consumption. And then the idea of foveation applies to not only rendering but also image sensing. If users can't really see things very clearly in the peripheral, well, why do we capture that with high fidelity to begin with? And that gave rise to the notion of foveated image sensing. And in fact, people, over 2 decades ago, people have started looking at a foveated image sensor where the pixel arrangement is non-uniform, highly concentrated and optimized for the fovea region. And over the years, people have applied this idea to different setups, things like compound microlens system for foveated imaging, as well as single pixel imaging, which has become more important with the rise of things like LiDAR. So we've talked a lot about foveation, but foveation is just one aspect of visual perception. There are many other aspects of visual perception that we could also leverage to optimize computation. For instance, saccades. Saccades refer to rapid eye movements between 2 consecutive fixations, and you can't really control yourself to avoid saccades unless you receive special training. But otherwise, you perform saccades, your eyes perform saccades all the time. In fact, the saccade rate is higher than your heart rate, so it's very frequent. You can't avoid it. Now, what's really interesting is that during saccades, during one particular saccade, your visual acuity is very low, and that's what we call saccadic suppression. And people perform very, very sophisticated psychophysical studies using the setup like what I'm showing you here. So this is a setup done by some of my colleagues at University of Rochester to precisely measure the saccadic movements as well as the visual perception during saccades. And saccadic suppression essentially provides another dimension to reduce the computation and the power because, well, your visual acuity is low, so your rendering and computation can sacrifice fidelity. Saliency is another aspect of visual perception that can be exploited. Essentially, in an environment, there are many salient objects that your eyes are naturally drawn to, and arguably those salient objects have higher priority in terms of data transmission or rendering. And we've done some work in this area to leverage saliency to reduce the bandwidth requirement of VR video streaming. So we take a VR video in the cloud, instead of just streaming it to the user, offline we would detect objects and track the trajectory of the objects with the hypothesis that those objects are salient objects that users are going to be really paying attention to or watching while they are watching the video. And then we generate smaller dedicated videos each for one particular object, and also the full video as well. And then at runtime, we monitor and calculate the user gaze to know which object that they're actually looking at, and then retrieve the small object video from the cloud, and that allows us to save the bandwidth. And if that turns out to be over time, if that's indeed the object that the user is tracking, then we have what we call FOV hit, and that reduce the bandwidth. In rare cases where we have an FOV miss, where the user is not really looking at the object that we thought that they were looking at, then we would have to retrieve the full video. But that's the penalty we pay. Yeah, and so this is another example of leveraging saliency, or another aspect of visual perception, to optimize the computing system. So to summarize, I'm advocating for a horizontal approach toward visual computing, where we have to co-design across different forms of information processing computing architectures that go beyond the conventional processor architecture to things like image sensors and optics and so on. These are just different forms of information processing or information processors that have to work together for visual computing systems to provide immersive services to users. And what I'm going to leave you with is, I think, an open challenge that we don't really have a good solution to, and that is how to come up with an agile workflow that allows us to explore the design and the enormous space constructed by these very different kinds of information processing architectures. Things like maybe a CAD tool or a high-level synthesis tool that can allow us to maybe even automatically generate an optimal configuration given an end-to-end application. And I think that's going to be hugely important going forward for the horizontal approach to really take off. And that concludes my talk. I'd like to thank you all for paying the attention, and I'd like to thank all my students. Some of them are listed here, and they've really done all the work, and I'm here to just talk about that. Thank you.
Hello, welcome to the architecture session. In this session, we will have 4 papers. The first one is from Institute of Computing Technology, Chinese Academy of Science, of which title is a routing-aware mapping method for data flow architectures. The second paper is optimizing Winograd convolution on GPUs via partial kernel fusion, which is authored by School of Computer, National University of Defense Technology. The third one is about adaptive low-cost loop expansion for modular scheduling, which is also from National University of Defense Technology. The last but not least one will present a novel systolic array accelerator with dynamic data flow for sparse gems in deep learning from National University of Defense Technology. Let's welcome the author of the first paper to present their work.
Hello everyone, my name is Fan Zhihua, and today my topic is a routing-aware mapping method for data flow architecture. I'm from the State Key Library of Processors from Institute of Computing Technology, Chinese Academy of Sciences, and I'm also with the University of Chinese Academy of Sciences. First, this is my outline. And today I will introduce the topic into 4 parts. First is background and motivation, and second is routing-aware mapping method. Third is evaluation, and fourth is conclusion. And first I will introduce the background and motivation for you. Data flow architecture is an emerging class of large-scale reconfigurable arrays designed for the compute intensity of modern analytical workloads. This figure illustrates a typical data flow architecture, which consists of a P-array, a configuration buffer, and a data buffer. The P-array is formed by multiple Ps that are connected by the network on chip. Each P is composed of a router, a local buffer, a register file, and several function units. With configurable data paths, data flow architectures can exploit multi-level parallelism and significantly improving their compute throughput and efficiency. And the picture shows what is our data flow architecture. When we use the data flow architecture, we need to have a data flow graph, we call that DFG, and map the DFG on the hardware substrate. And what we need to know is, first, DFG nodes represent computing DFG edges represent data dependence between nodes, and the second, DFG mapping has a significant influence on the performance. And the lower picture shows how programmers first divide the big computation tasks into many subtasks like A, B, C, D, E, and then the compiler will generate the code and divide the code into many blocks like A, B, C, D. You can see the relationship between them, and they have dependencies to guide the hardware to calculate. Third, the DFG nodes will be mapped onto the P array like C. A and B are on one P and C, D, E are on separate PEs. We need to know that DFG mapping algorithms have a significant impact on the performance of data flow architectures because they will guide how the function units calculate and when will they calculate and how they will calculate, and they will guide how the data will flow on the whole P array. Well, then I'll show you the conventional and the routine-aware mapping method. In recent years, many approaches have been proposed for mapping kernels onto data flow architectures. In general, these methods can be divided into two main categories: depth-based methods and breadth-based methods. The depth-based mapping approaches map DFG nodes by depth first order and aim to reduce the error at the data transmission distance. The breadth-based mapping algorithms map DFG nodes by breadth first order. We can see in the picture the three kind of mechanisms. The first depth-based mechanism will cause 5 trans latency, and the second will cause 7 trans latency. And in our use our mechanism, RAM will only cause 3 trans latency. Ours map the node to the PE which has the minimal computing cost and routing cost. As shown in the picture, RLBA achieves the shortest execution latency. When designing a DFG mapping algorithm, both hardware resources and data flow graph characteristics should be considered together to explore better data flow graph mapping schemes. The hardware resources insights means it is necessary to consider the heterogeneity of hardware resources. The DFG characteristics insights refers to the need to consider not only the data transmission distance between the current node and its upstream node, but also the data dependency between the nodes and its downstream nodes. So we are sure that the hardware resource allocation and the data flow graph is the two main points when we are designing on the data flow architecture. Second is the routing-aware mapping method, which is our design point. Well, first, the algorithm 1 is our first algorithm, which is our routing-aware mapping method. Based on the above analysis, we propose a novel DFG mapping method which can improve routing load balancing as shown in algorithm 1. It is a search algorithm and incorporates efficient pruning, which reduces the execution time of the mapping algorithm. The algorithm 1 first sorts all the nodes in the data flow graph in the breadth first order. All nodes are sorted based on their position in the DFG, and data dependencies between these nodes are preserved. The BFS sort function sorts the nodes and stores the order in SD. When evaluating the node calls, we treat the node and its predecessor and successor nodes as a group. We evaluate the cost of the entire group and choose the mapping scheme with the least cost. The select candidate nodes function selects candidate nodes from the SD. Then the algorithm 1 finds all mappable schemes of the group by the getMapping function. The getMapping cost function is used to calculate the cost of each scheme. Algorithm 1 selects the scheme with the lowest cost as the mapping result. Well, in this slide, I will introduce the algorithm 2. The detail of getting mapping cost is exhibited in algorithm 2. The input of this algorithm is the node group and their mapping relationship to a set of PEs. The below three figures will show how the nodes are mapped onto PEs through times. Well, after introducing our design point, this is the evaluation. This is the evaluation part. Well, we first develop a cycle rate accurate architecture simulator. We select important workloads from Polybench, MIBench, and Spec 2000 for experiment. We choose two state-of-the-art DFG mapping methods to compare with our algorithm. PBCT is a representative depth space method to map the DFG to the hardware. It aims to map the DFG nodes to the closest PE and improve computing resources utilization. REGMap is a typical breadth-based DFG mapping method. It maps the data flow nodes to different PEs as much as possible to obtain load balancing of PEs and achieve higher parallelism. We use the number of instructions executed per cycle IPC to evaluate the execution performance of the data flow architecture. The higher the IPC, the better the performance of the kernel. And the figure demonstrates the IPC comparison normalized to PBCT. RLBA gains a 1.65 times geo-mean IPC improvement over PBCT and 1.45 times improvement over REGMap. After that, I will introduce the scalability and cost of our design. In our approach design, we do not make any assumption on PE array size and interconnection topology so that our approach can be applied to various data flow architectures. So this is our scalability analysis. To verify this, we first modify the architecture with typically network topologies, 2D mesh, and 4D torus. Second, we modify the size of PE array to 2 times 2, 4 times 4, and 8 times 8. The interconnection topology is the most typical 2D mesh. We achieve the performance results shown in this figure. It is worth noting that the improvement brought up by our approach has tapered with the increase in the size in many cases. The reason is that the computing resources is the bottleneck when the size is small. In summary, our method has good scalability. Since the compilation time decides whether the algorithm is practical, we report this indication in the lower figure, which is achieved on a Zen 4116 CPU. To achieve a valid mapping with a better performance, ILBA evaluates both computing cost and routing cost, which may cause longer compilation time than other methods. The ratio of compile time to execution time is very small, so the cost AQ2 of compilation is acceptable. And here comes our conclusion. First, we design a DFG mapping algorithm which first focuses on the influence of predecessor and successor nodes, considers the computation of computing resources and the routing cost. And second, the experiments demonstrate that our method can achieve up to 2.06 times geo-mean performance improvement, and 12.8% energy consumption reduction compared to the state-of-the-art methods. That's all. Thank you.
Hello everyone, I'm Zhang Jing from National University of Defense Technology. I'm happy here to present our work optimizing integrated convolution on GPUs via partial kernel fusion. Convolution neural network, or CNN, is one of the representative algorithms of artificial intelligence, and its core component is the convolution operator. According to the different implementations, CNNs are mainly divided into 4 types: direct convolution, IM2-core-based convolution, FFT-based convolution, and vinaigrette-based convolution. Direct convolution is the calculation according to the definition. In this example, the size of the convolution kernel is R squared, and the size of the input matrix is M squared. A total of M squared times R squared multiplication operations are required to get the output. The calculation efficiency of direct convolution is very low, and the continuity of data access is not good. Expand the window of each calculation into a vector, and the operation becomes the inner product, which is called image to column or IM2-core. In this way, the arithmetic strength and performance is largely improved. However, in the case of a single channel, the number of multiplication required is not changed. So researchers began to study fast convolution algorithms that can reduce the number of multiplications. In 1980, Vinaigrette proposed a minimum filtering algorithm for finite impulse response and reduced the minimum multiplication number to n plus r minus 1. Levine found its value in accelerating convolution neural networks in 2015. Taking F23 as an example, if the input length G is 4 and the convolution kernel length D is 3, then G can be overlapped twice on D to get 2 outputs, Y0 and Y1. The algorithm introduces 4 numbers, M1 to M4, which can be calculated in advance. Then using M to calculate Y0 and Y1 only needs addition and subtraction. After such transformation, the number of multiplications is reduced from 6 to 4, reaching the minimum number for convolution. Expanding to 2-dimension case, the number of multiplication reduced to the circle of m plus r minus 1. This figure shows the 4 steps of vinaigrette convolution. The first 2 steps is to transform input tensor and kernel to vinaigrette domain, then multiply the tensor and convolution kernel by the corresponding byte to obtain the output. Lastly, restore the vinaigrette domain output to the future mapping space to obtain the final output. Related work on vinaigrette convolution is mainly divided into 3 aspects: numerical stability, optimization, implementations on GPU. The main reason for choosing vinaigrette convolution as research object is the inefficient implementation in CUDN, and there is little research on its optimization on GPU. Our work is optimized from these 2 points using high-speed tensor core and fusing Winograd calculations. This table shows the parameter of a Winograd convolution operator. Computations in the Winograd convolution are concentrated in the EWMM stage with low arithmetic intensity, which is 1/12, far lower than the operation bandwidth ratio of GPU. Jia proposed to convert EWMM stage to improve the arithmetic intensity. The effect is very impressive. This figure shows the process of BGM. In order to use tensor core to accelerate BGM, we construct a computation in the BGM algorithm that can match the tensor intrinsic. BGM still remains 2 problems. One is the cost of thread synchronization, and the other is that BGM cannot run efficiently on GPU due to the limit of data type. In order to eliminate the cost of synchronization, we improve BGM to sync-free BGM. We tile the workload along the Intel dimensions and allocate uptime blocks to thread blocks, while the data in the batch dimension is allocated to the same thread block. The data accessed by each web is consistent with the data used in the calculation. In this way, each web can perform instruction immediately after reading the corresponding tile, without waiting for other webs to reach the synchronization point. This slide shows the results of the experiment. The 5 sets of tests come from simple EWMM, simple BGM, BGM using scheduling algorithm, BGM using scheduling algorithm and tensor core, sync-free BGM. As can be seen, the performance has been significantly improved after using BGM, especially after the introduction of tensor core. There are 2 fusion technologies. One is circular fusion, and other is the operation fusion. Circular fusion uses the same circular axis to fuse multiple cycles together. Here, we use pseudocode to show an example of circular fusion, which combines 3 circular into 1. Tensor virtual machine implements the neural network as a computational graph, and each stage of the graph corresponding to an operator. Operators are divided into 4 types in TVM, except for the last one. Other operators can be fused in a certain extent. For example, the classical convolution, bench standardization, and radio activation can be merged into a new convolution operator. We made an in-depth analysis of Winograd and found that it cannot achieve circular fusion and operator fusion. However, there is obvious data correlation between the 4 stages of Winograd convolution. So we can use the multi-level cache, multi-level memory of the GPU to temporarily store the intermediate results between stages. Therefore, we propose 2 new fusion strategies. Figure C and D show our 2 fusion strategies. which use shared memory or the last level cache to temporarily store intermediate data. We apply these two methods to vinaigrette convolution. In this work, we have chosen input transformation and BGM stage for fusion. The two fusion strategies are implemented by using shared keyword and memory synchronization instruction respectively. The experiment measures the performance improvement of FP16 vinaigrette convolution using PKF technology. The four groups of data are benchmark, sync-free technology, shared memory, and last level cache. The results shows that both sync-free technology and PKF technology can improve the performance of vinaigrette convolution to a certain extent. For PKF technology, the acceleration effect on shared memory is very significant. There are two problems to implement on TVM. First, the TVM automatically inserts thread synchronization instructions in the process of generating code. Second, the schedule primitive in TVM cannot realize the two new proposed fusion strategies. So we present a decoupled implementation. The vinaigrette convolution prototype was first created using TVM. The code is then processed to apply sync-free and PKF technology. The resulting CUDA code is compiled by NVCC to generate the vinaigrette workload. The advantage of this approach is that we do not need to modify the TVM codebase, but the disadvantage is obvious. We can only get a single optimized vinaigrette convolution code. So we implement a code reconstructor named PKF reconstructor. Its core idea is to use regular expressions to match the corresponding code, then remove the corresponding thread synchronization instruction, build a new kernel and insert input transformation and BGM code. Finally, insert the ensemble kernel into vinaigrette convolution operator test template and modify the relevant constant value. This slide shows our experimental environment. We code the convolution operators in MXZ zoo and select the convolution operators with the highest frequency and merge different feature mapping size. We use FP16 and int8 as data types, implemented in shared memory and last level cache respectively. The final baseline is the vinaigrette convolution implementation on CUDN. We choose native vinaigrette convolution on the TVM as a control, averaging 1,000 tests per group. Experimental results shows that all 4 PKF implementations on FP16 achieve considerable performance compared to the CUDN. Factor 16 on shared memory perform best, achieving a speed up of 9.99 times to 13.69 times. TVM is a bit better than CUDN. Our experimentation is far more than TVM. That is all. Thank you.
Hello everyone, This is Zhonghong Li. I'm from National University of Defense Technology. Today, I'm here for a presentation on adaptive low-cost loop expansion for module scheduling. The presentation is divided into 3 parts, and the first part is the overview of the paper. Very long instruction word was first proposed by George Fisher in 1983. Based on the idea of instruction-level parallelism, it combines multiple independent instructions into a long instruction. VOIW architecture simplifies hardware design and brings new challenges to static scheduling technology. Module scheduling is used to explore the instruction-level parallelism for loop optimization. However, for highly integrated VOW machine, traditional frameworks cannot fully utilize resources to produce the best solution. Loop unrolling cannot only reduce or even eliminate the overhead of loop drums, but also expand the sense of loop body for more scheduling opportunities. Well, loop unrolling can reduce the number of counts and jumps, providing more opportunities for subsequent scheduling. However, excessive unrolling will increase register requirements and lead to failed scheduling. Therefore, 2 major challenges are how to find an optimal unroll factor and how to schedule unrolled loops for best performance. The high register pressure is the side effect of module scheduling, which means that the benefit from pipeline are likely to be reduced or even lost due to register splitting. Therefore, the next challenge is how to relieve the register pressure. In addition, take account of efficiency problem. The last challenge is how to reduce the overhead of scheduling. To address the above issues, in the paper, we proposed the expanded model scheduling, which is called EMS for short. Next, we are going to the introduction of our method. Module scheduling is an implementation of software pipelining. The scheduling for each iteration is divided into several stages with II cycles each, and the benefit derives from the repetitive execution of a pipelined kernel. A code scheme of module scheduled loop is shown in the figure. From the figure, we can see that the target loop is divided into 3 parts: core log, kernel, and epilogue. While the execution time required for a loop iteration is reduced from 14 cycles to 4 cycles. Data dependence graph is a directed graph that describes the data dependency among operations. In EMS, DDG consists of 5 elements, where HU is the head of operation U, which is defined as the maximum distance from operation U to some operation without successors. Unlike methods that treat scheduling and loop unrolling as independent of each other, the scheduling processor in EMS is jointly directed by EC and II, striving to achieve maximum resource utilization while minimizing iteration interval. To prevent excessive loop expansion, EC should be less than the minimum number of iterations, and for each EC, iteration interval starts from a minimum estimated value and increases by the step of 1. MII is determined by 2 bounds. One bound derives from the critical resource usage, called RES-MII, while the other bound derives from the critical recurrence circuit, called REC-MII. EMS is designed to provide a code generation framework capable of optimizing loops for realistic machine models. Therefore, EMS divides loop iterations into 2 parts, pipelining and non-pipelining. The pipelining framework of EMS is shown in Figure 2. First, EMS will build a data dependence graph for the target loop, and then perform the iteration of EC and II. For each iteration, the target loop will be copied EC times, and the EMS will perform scheduling, resolving, expansion faults, and completing the MRT in turn. Then, an example will be used to illustrate the workflow of EMS. First, we build a virtual processor and its instruction set as shown in Table 1. Table 1 provides function units available for each instruction and the number of cycles required for execution. Based on the above instruction set, we map the sample program to assembly code. It should be noted that this assembly code is only used to describe the logic of the program. Data dependency analysis on the target loop is the first step of EMS. In this stage, EMS will obtain two strongly connected graphs, as shown in Figure 3. The first graph describes the dependency of the loop body, while the second graph describes the dependency of the loop counting chain. Based on the first graph, REC MII equals to 1 and the RESP equals to 1.5. By performing the critical path algorithm on the first data dependency graph, we can divide operations into critical operations and non-critical operations. Since the critical path algorithm can only deal with directed cyclic graphs, EMS only consider the edges where the iteration distance is equal to 0. In addition, for each operation, their height, input degree, and output degree in the graph are listed in the table 2. Loop expansion is the second step. Since the number of loop iterations is 1024, EC can be set from 0 to 1023. When we set EC to 2, then RES MII equals to 5, MII equals to 5, and the iteration of II starts from 5. The process of loop expansion twice is shown in the figure. From the figure, we can see that expansion process is performed on the target DDG instead of the loop itself. In step 3, EMS needs to answer two questions. One is in what order the operations should be selected, and the other is in which time slot the operations should be placed. In the selection phase, EMS first divides all operations into several groups based on their own height in the graph, and then selects the group with the largest height for scheduling. 3 kinds of objects are scheduled in each round, namely the current critical operations, the latency non-critical operations, and the current non-critical operations. In the placement phase, EMS focused on data dependencies and resource constraints. To minimize the lifetime of all variables, each operation is placed as close as possible to its predecessors and successors. Before scheduling, EMS needs to initialize the model reservation table, which is called MIT for short. The structure of MIT is shown in the figure 4. In MIT, each cell represents a time slot. Instructions in the same time slot can be executed in parallel. In the first round of scheduling, according to the operation information table, critical operations N1 and N2 in expansion layers 1, 2, 3 will be scheduled to the MIT. In the second round, critical operations N3 in layers 1, 2, 3 will be scheduled to the MIT. In the third round of scheduling, non-critical operation N4 will be placed in CN list, while critical operation N5 will be placed in CC list. In the fourth round of scheduling, critical operation N6 will be scheduled to the MIT, and then the operation N4 will be scheduled. In the last round, critical operations N7 in expansion layers 1, 2, 3 will be scheduled to the MIT. So far, all operations have been scheduled, and the stage count SC is equal to 4. In the face of resuming expansion force, the problem of data conflicts among expansion layers will be resolved. For variable conflicts, we take variable T02 as an example. T02 is defined in N1 and used in N3 and N4. According to the time slots of N1, N3, and N4 in the MIT, variable T01 leave range in layer 1 is 6, 7, in layer 2 is 7, 8, and in layer 3 is 8, 9. As a result, there are data conflicts between adjacent layers. One way to eliminate the above conflicts is to rename T02 in any two expansion layers. In the time slot 18, two strong instructions access the same address, so EMS modifies their address operations respectively. In the final step, EMS copies each operation in the MIT for 3 times and then inserts the loop counting chain. By the way, N9 is placed in the time slot 14 and its jumping action will be triggered at the end of the time slot 19. The result is shown in the figure. From the figure, we can see that pipeline loop requires 338 iterations in total, and each iteration takes 5 cycles. In this part, I will show you the performance of our method. We adapted EMS to one of the MT3000 acceleration codes and carried out experiments based on 16 innermost loops from a small number of critical programs in the field of signal processing. We compare EMS with 3 classical methods, including base OPT top-down and U top-down. For evaluation measures, we use II register requirements, average resource utilization, and total bits to measure the performance. Overall, EMS achieves the minimum iteration interval on 6 programs and improves the best performance of all innermost loops by at least 14 times. In terms of resource utilization, EMS outperforms other methods on 6 programs. The reason for the better resource utilization of top-down on SEAL is that RESU takes loop counting chain into account. Otherwise, the resource utilization of EMS is the same as that of top-down. In terms of register requirements, EMS requires fewer registers than U top-down, and due to loop expansion on the 4 programs, EMS consumes more registers than base OPT and top-down, but the register pressure is still under control. That's all for today's presentation. Thank you for your attention.
Hello everyone, the topic of my report is SADD, a lower systolic area accelerator with dynamic data flow for sparse GMM in deep learning. I'm going to report in 5 parts. Introduction, background, SADD architecture evaluation conclusion. In recent years, deep learning has become very popular. Different deep learning models are widely used in several important fields. Before the appearance of dedicated neural network processors, the running of deep learning algorithms mainly used the GPU and CPU. The explosion of big data applications have propelled the development of deep learning, but it also poses serious challenges to the data processing speed and scalability of traditional computer systems. Traditional one-Neumann computer architectures are relatively inflexible, with separate processing and data storage components. Frequent data movement between traditional architecture processors and off-chip memory limits the system performance and energy efficiency. Deep learning accelerators are usually composed of a large number of highly parallel computing and storage units, which can accelerate the computing tasks in deep learning. The core computational tasks of most deep learning models in training and inference is the general matrix multiplication. Accelerating the GMM has become a major goal of hardware accelerator design. Google's TPU is a typical GMM accelerator. The TPU uses a systolic array as its hardware structure. A systolic array is a two-dimensional array composed of p's, and the data flow only between p's. Historical array can reduce the exchange of the data with the global cache and can reduce the data loading time, so it can reduce energy consumption and speed up the GMM. Historical arrays can efficiently compute the dense GMM but cannot take advantage of sparsity. Compared to accelerators that support sparsity, the TPU introduces additional computation time and energy consumption when running sparse GMM. In this paper, we design and implement the SADD, a state-of-the-art systolic array accelerator that supports sparsity and dynamic data flow. This paper makes the following contributions. First, we propose the GSMC method to compress the sparse matrix in the systolic array. Based on the GSMC method, we propose the SS and SWS to make systolic arrays about sparsity. Second, we propose the SADD and a state-of-the-art systolic accelerator SADD. The SADD used in the SADD combines the SS and SWS, which can dynamically switch the data flow according to the weight matrix size and input matrix size. Third, we analyze the performance of the systolic arrays used in the WS, IS, OS, SS, SWS, and SDD with different sizes of GMMs, and shows that the SDD can achieve high performance in any computing environment. Fourth, we implement and evaluate the SADD. The performance of the SADD is twice better than the TPU. When running the sparse accelerator and the SADD brings only a small amount of additional hardware overhead. Matrix multiplication in deep learning workloads. At present, the neural network processor usually converts the convolution operation into the matrix multiplication. Therefore, the GMM operation is the core computation operation of deep learning training and inference. In particular, the GMM operation can account for more than 70% of the computing cycle. So, accelerating the GMM is the major goal of hardware acceleration. Sparsity in deep learning workloads. Tensors in deep learning are always sparse. Multiple factors induce the sparsity to the tensors in deep learning models. The design of deep learning accelerators need to take into account the sparsity of tensors. Accelerators taking advantage of sparsity can eliminate efficiency computations and improve performance. By processing only operations involve non-zero values, the execution time and energy consumption of computations can be reduced. Meanwhile, by storing only non-zero values, the memory requirements can be reduced, reducing both on-chip and off-chip memory access counts. Group structure maintains compression. The row-wise GSMC. Compression sparse tensors can reduce the storage and communication requirements of the processor. To compress sparse metrics in the historical area, we propose a new compression method, the group structure maintained compression (GSMC). This figure illustrates the GSMC method. In the row-wise GSMC, some elements in a row are defined as a group. The left boundary of a group is the leftmost non-zero value in this row, and the right boundary is the rightmost non-zero value in this row. Each row has a group if there is a space above. Groups are moved up without changing the column. The SWS fixes the weight matrix into pieces of the historical area. Before the computation, the uncompressed weight matrix is fixed into pieces, where the P input matrix is compressed by the row-wise GSMC. The compressed input matrix is streamed row-wise to the left of the historical area and continues to the right after being processed by PEs. After the PE processes the elements of the input matrix, the partial sum is generated. The partial sum is passed down after being processed by PEs. After processing a group of elements, the result leaves the historical area via the forwarding link rather than passed down. The performance of SS and SWS with different GMM sets. This figure shows the performance comparison of the SS and SWS. The sparsity in the experiment is 70%. The three numbers on the horizontal axis represent the size of the GMM. If the size of the input matrix is smaller than the size of the weight matrix, the performance of the SS is higher. Otherwise, the performance of the SWS is higher. We designed the SADD, a historical area accelerator that supports sparsity and dynamic data flow. The data flow used in the SADD is a SDD, as shown in this figure. The SADD includes input matrix wafer, weight matrix wafer, data flow selector, Structured compression unit, systolic array, accumulator. Experimental method. We compare the performance of the SDD with other data flows in systolic array with different GMM size. We implement various systolic array accelerators using the WS, IS, OS, SIS, SWS, and SDD. We implement the above systolic array accelerators using RTL Verilog HDR. Compression of the SAD and the TPU. Due to the small scale of the systolic array accelerator we implemented, we choose the small-scale neural network AlexNet. The convolution operation in the AlexNet is converted to GMM, and we introduce 70% sparsity to these GMMs in our experiments. This figure shows the performance compression of the SADD and the TPU. On average, due to the support of the sparsity and the dynamic data flow, the performance of the SADD is twice better than the TPU. Hardware cost analysis. We compare the hardware overhead of the SADD with the WS, IS, and OS systolic arrays. Each of them contains 64 PEs, and the experimental results is shown in this table. In the OS, because the result needs to be saved in PEs, there are additional registers. So, the hardware overhead of the OS is higher than that of the WS and the IS. The increase in the hardware results of the SADD is mainly used for the structured compression unit and the data flow selector. Compared to the WS, IS, and OS systolic array accelerators, the SADD has about 10% increase in the hardware overhead. This overhead is acceptable. Conclusion. In this paper, we designed and implemented the SADD, a state-of-the-art systolic array accelerator that supports sparsity and dynamic data flow. During the design of the SADD, we proposed the group structure maintained compression (GSMC) method to compress the sparse matrix, and we proposed the sparsity supported weight stationary data flow (SWS), the sparsity supported input stationary data flow (SIS), and the sparsity supported dynamic data flow to support the sparsity in the systolic array. Thanks for listening, everyone.
Welcome to the deep learning session. This session will have 6 papers. The first one is from College of Computer Science and Technology, National University of Defense Technology, of which title is NeuProma, a tool train for mapping large-scale spiking convolutional neural network onto neuromorphic processor. The second paper is an efficient design paradigm of an accelerator architecture based on FPGA from University of Science and the Technology of China. The third one is about a lightweight programmable ML training framework via serverless paradigm from Institute of Computing Technology, Chinese Academy of Science. The fourth and fifth paper are both from University of Shanghai for Science and Technology. The fourth paper is about discrete rank pruning for neural network The fifth one will talk about a transformer-based predictive page migration mechanism for heterogeneous memory. The last one will present hardware acceleration for 1D CNN-based real-time edge computing. Let's welcome the first paper's author to show their work.
Hello, everyone. I'm Xiao Chao. I come from National University of Defense Technology in China. The title of my presentation is Neuromer, a tool chain for mapping large-scale spiking convolutional neural networks onto neuromorphic processor. The content of my presentation contains 8 parts. Spiking neural network, the third generation of artificial neural network, was proposed to mimic how information is encoded and processed in the human brain. Spiking neurons in the spiking neural networks communicate with each other by sending spikes. Spiking convolutional neural network, which has the CNN-like structure and adopts the spiking neuron as the fundamental computing element, has been applied to many machine learning tasks. Neuromorphic processors, the new generation of brain-inspired long-volume computing systems, have the potential to perform complex computations with more energy efficiency than conventional architectures. The neuromorphic processors are generally multiple systems and adopt the network-on-chip as the communication framework. Although the neuromorphic processors provide parallel communication, a long-optimized mapping of spiking neural networks to the neuromorphic processor may increase the spike communication traffic between neuromorphic cores, leading to NOC congestion and impairing execution performance. Besides, the limited computing resources and on-chip memory can only support the execution of a limited number of neurons. Our proposed approach is shown in the bottom of the slide. Neuromer contains 3 parts: splitting, partitioning, and mapping. Splitting is to divide the large-scale network into several subnetworks so that each subnetwork can be accommodated on the processor. Partitioning is to partition the subnetworks into multiple clusters so that each cluster can be executed on a single core, while reducing the spike messages on NOC. Mapping is a process to search for the cluster-to-core mapping scheme while improving the NOC congestion. We will now start talking about these steps in more details. The different splitting schemes lead to different spike communication traffic between subnetworks, which impacts the off-chip and on-chip data exchange. Here, we introduce 3 splitting methods. The position of each neuron can be represented as X, Y, Z, L. X and Y are the coordinates of the pixel in the feature map. Z is the feature map index, and L is the layer index in the whole network. The sequential splitting strategy just divides the network sequentially according to the coordinates. The pixel splitting strategy distributes the neurons located at the same pixel into the same subnetwork. The connections in the spiking convolutional neural networks are regular in a set. For the convolutional operation, the neurons located at the same pixel receive spikes from the same presynaptic neurons in the preceding layer. For the pooling operation, although the neurons have different presynaptic neurons, those presynaptic neurons are located at the same pixels. Based on this observation, the pixel splitting strategy traverses every pixel of the feature maps sequentially and puts the neurons located at the same pixel into the same subnet work. The sequential and pixel splitting strategies divide the networks layer by layer. After the execution of the preceding layer, the processor should record the firing information of the preceding layer, that is, the intermediate results, and store the intermediate results in the off-chip memory. When the following layer starts the computing, the processor should load the spike trains from the off-chip to the on-chip. Based on the pixel splitting strategy, the linkage splitting strategy places the connected neurons from different layers in the same subnetwork. After the initial large-scale network is split into multiple subnetworks, each subnetwork can be executed on the neuromorphic processor at once. The next step is to partition each subnetwork into multiple clusters so that each cluster can be executed on a single core. We partition all subnetworks according to a particular order. We'll first define 3 states of neurons. A neuron in preparation means that its presynaptic neurons have not finished the computation. A neuron waiting for execution means that its presynaptic neurons have finished the computation. A neuron completing execution means that it has accomplished its computation. We build an empty stack and push the neurons in the first layer into the stack. Then, we pop the first neuron from the stack and push new neurons into the stack. We repeat this process until the stack is empty. The order of neurons popping from the stack is the order of computation. NuPromer generates the computation order for the initial network instead of each subnetwork. NuPromer partitions each subnetwork sequentially according to the computing order. In the mapping stage, NuPromer minimizes the maximum workload of routers. For every unmapped cluster, we explore all unallocated cores. We pre-map the current cluster on the selected core, simulate the spike communication according to the routing algorithm adopted by the target neuromorphic processor, and calculate the workloads of all routers. Then, by comparing with the historical optimal record, we choose the better mapping scheme, where the maximum workload of routers is smaller. We use 6 spiking convolutional neural network-based applications to evaluate our proposed approach. Column 2, 3, and 4 report the number of neurons, the number of synapses, and the number of subnetworks after splitting the 6 applications respectively. We compare the 2 state-of-the-art approaches, SpearMap and SLEEP. We first evaluate the data exchange volume between the off-chip and on-chip memory. We show that the linkage splitting strategy outperforms the sequential and pixel splitting strategies. It not only decreases the memory needs to store the intermediate results, but also decreases the data exchange volume between the off-chip and on-chip memory. Next, we evaluate the spec count. It is the total number of spec messages on NOC. After the linkage splitting strategies, we use SPMF, SNP, and NeuPromer to map the separate works onto the neuromorphic processors. Compared with SPMF and SNP, NeuPromer achieves the minimum amount of spec messages. On average, 85% and 42% lower than SPMF and SNP respectively. In terms of the spec latency and energy consumption, because of the remarkable reduction in the spec messages, NeuPromer has the lowest spec latency and energy consumption. We also evaluate the execution time. In the partitioning and mapping stage, NeuPromer achieves 2012 lower execution time than SPMF, 149 lower execution time than SNP, respectively. In this paper, we introduce NeuPromer, a tool chain to map large-scale spiking convolutional neural networks to the neuromorphic processor. NeuPromer maps the large-scale spiking neural networks in 3 steps: splitting, partitioning, and mapping. The linkage splitting strategy can reduce the intermediate results, which reduces the memory needs and the exchange volume of intermediate results between the off-chip and on-chip memory. The partitioning algorithm of NeuPromer significantly reduces the spec messages on NOC, improving the spec latency and energy consumption. In the mapping stage, NeuPromer minimizes the maximum workload of routers. We have conducted experiments with 6 spiking convolutional neural networks and demonstrated a significant increase in performance over current practices. Thank you.
Hello everyone, my name is Chen Wang and I'm a PhD student in the University of Science and Technology of China, College of Computer Science and Technology. I'm honored to be invited to NPC 2022 in CCF HPC China. Today I will share my work about design method of accelerator, which is called multi-cluster, an efficient design paradigm of an accelerator architecture based on FPGA. Here is the outline. I will introduce our work from 4 parts: introduction, background, and multi-cluster method and experiment. With several development of neural network models, it also brings some difficulties in processing this application, like large computation, huge parameters, complex workflow. Therefore, choosing a good platform for this complex computing application is essential. FPGA is great due to the low power consumption and reconfigurability. Is gradually becoming an accelerating platform that balances power and performance. Optimized for the computational process of the application and the data in the model, FPGA can achieve high parallelism and simplify the logic. In the current implementation of neural network accelerator based on FPGA, it shows that FPGA has many advantages compared with CPU, GPU, and ASIC. As shown in the figure 2, it explains the current trend of using FPGA to accelerate the neural network applications in scientific research. And nowadays, the organization of most FPGA-based accelerator heterogeneous accelerator system is shown in the figure 3. The CPU side is responsible for the control and the data scheduling of the overall computing, while the FPGA side is responsible for the parallel computing results, and its design pattern of hardware architecture is mainly divided into two categories: overlap and stream. As shown in the figure 4, the sort of the overlap method is mainly to design a reusable big processing engine to perform the common parts of the algorithm. At the same time, the hardware control and operation scheduling are executed by the host code in the R player. Another design pattern stream is shown in the figure 5. It outside to the overlap. It implements different hardware units for each computing parts in the calculation flow for the target algorithm or the optimizer to take advantage of inter-block parallelism. The computing units are connected in the order of algorithm. After the data flows through each unit, the calculation can be complete, and the intermediate results flow into the next unit. Therefore, the advantage of overlap is flexible, which we do not need to be reconfigured when the input mode has changed, but the computing type has not changed. However, due to control mechanism like the general processor, it is not easy to achieve maximum efficiency in computing. Because this one-size-fits-all approach may lead to the inconsistent final performance on network models with different workload characteristics. And the advantage of stream part is easy to achieve high performance because for the different characteristics in the different computing parts, we can use different ways to optimize the implementation and the parallelism scheme in each hardware kernel. However, the disadvantage of stream part is that it's not flexible, and we should design new hardware computing units for different network models. Therefore, in this work, we proposed a new design paradigm for the neural network accelerator based on FPGA called multi-cluster. As shown in the figure 6, we combine the characteristic of the above two design paradigms, minimize external scaling overhead, and achieve high performance. First, we supplied the network model into slices and contain a sequence of operations. Then different cores are designed to map this part for efficient execution. The fine-grained pipeline is performed inside the cores. Multi-cores are executed by software scheduling and implementing a core-scanned pipeline. We investigate the main difference between these two design paradigms in the past and find that the computation to communication ratio (CTC) is the key factor, as shown in the figure 7, because the value of CTC represents the maximum number of calculation results that can be produced by unit data in some calculation model. On the same computation model, the larger value number means the fewer data interactions, and a small value means the stronger correlation of data. Therefore, the difference between the network layer with the different CTC in the same computing models leads to the difference in potential parallel performance. So the overlap structure is hard to achieve high computational efficiency, while in the stream part, the specified optimization for each layer will significantly improve the overall performance. Based on the sort, we design a division method to split the neural network model by the value of CTC. First, we split the network into several parts, and each contains a sequence of network layer. Then we can calculate the CTC value for each layer and the performance subsequence division according to the CTC value. Finally, the layer with similar CTC in the same subsequence will be classed into the same processing engine with suitable configure. The MC paradigm is different from the stream, which maps all the computing processors with and also different with the overlap, which structure the common computing features. It is designed that balances two methods to explore optimal computational performance. After we have split the process graph of the network model into the several common subsequences according to the CDC value, we will design architecture support different subsequences executed on multi-PEs, all of which can execute a part of the sequential operations in the network. As shown in the figure 8, we give the overall architecture design with the example analysis. In the software layer, we can combine the different PE with some order to complete the calculation of different network models. On the hardware level, this sequential operations runs in a predetermined order inside the PE with repeating several times. In design space exploration section, because of the equation of PE performance, it can be found that the overall performance of MC is affected by maximum latency of each computing unit and repeating times. Therefore, to optimize computing performance and hardware utilization, we use workload equilibrium to measure the results of the optimization. Therefore, we proposed a workload equilibrium algorithm based on the greedy stretch to complete the DSE task. As shown in the right, we try to get the implementation of the computing unit with our search algorithm according to the exciting conditions. As shown in the figure 9, we give the scheduling schedule for the provides for the example architecture. Different color represent different data sources. The solid box represent processing, while the dotted box represent temporal reels with the same PE. In the inter-PE levels, the software side need to consider how to logically connect the calculations of these PEs to achieve algorithm's result, and different data sources process alternately with different PE to cover the time cost. Moreover, in intra-PE level, some PE is executing several times to achieve the result that inner result with inner pipeline to optimize the time cost. And in this way, computing resources can fully utilized, and the external scheduling strategy is easy to achieve. In the experiment section, we implement MC on the settings LVU50 FPGA with sweetest to flow. Then we perform the comprehension comparison with the result of CPU, GPU, and other FPGA accelerators. Here is our experiment setup. The compared results with the CPU and GPU as shown in the table first. Furthermore, we give the resource utilization of the accelerator with the MC pattern shown in the table 2. For performance, our accelerator achieve about 40 times compared with CPU implementation. Compared to GPU implementation, we only achieve half time performance. But however, we have achieved about 20 times and 8 times energy benefit compared to CPU and GPU. As the implementation shown in the table 3, we list some related work that design accelerator for AlexNet and VGG. To compare with some AlexNet accelerator works 4 and 5 with ours, we achieve about 1.4 to 5.5 times improvement in throughput and 1.5 to 6.3 times in calculation efficiency. Furthermore, their low efficiency is that the overlap type accelerator design brings a lot of control overhead and avoid cost of data fragmentation in parallelism computation. Moreover, because of the stream pattern, the work 3 and 7 achieve high performance values, but we also maintain the same level of calculation efficiency when running VGG. This comparison also showing that our MC architecture can obtain similar computation efficiency in the stream tab. Moreover, compared with the other accelerator work 6 and 8, we achieve about 1.9 to 5.5 times in throughput and 1.7 to 2.6 times in calculation efficiency. It can prove that our paradigm is efficient and for designing network at accelerator architecture based on FPGA. And here is our work's conclusion. This is some reference of these slides. And thank you for your listening. If you have any question, you could ask me here or send an email to me. Thank you.
Hello everyone, my name is Tan Wenting. I work as a PhD student at the Institute of Computing Technology, Chinese Academy of Sciences. I'm honored to have the chance to address you of our work, and my topic is TrainFlow, a lightweight programmable ML training framework via service paradigm. The outline of my talk as follows. The first part, I want to introduce the motivation of this work. I will start by 3 challenges that the distributed ML systems has. First, the ML training moves towards the trend of involving more data, larger parameters, and stronger computing power, such as model broad large contains 387 million parameters. It naturally relies on increasingly more computer cost and time. So, distributed ML training is resource hungry. Second, it is hard to manage facilities for distributed ML training. Before we start running the training code, we need to prepare clusters, configure communication strategy, and install ML libraries. These are a huge bound for data scientists. Third, it is hard to guarantee distributed training performance due to the dynamical cloud resources, such as the part of the workloads may be down or lost connection. While serverless computing recently emerged as a promising paradigm for training, as it lifted the burden of managing cloud resources. and it also offers a lower pay-as-use cost model and can be more cost-effective compared to traditional server cloud computing. One type of service, the function as a service, FaaS, has been offered by major cloud service providers such as AWS Lambda, Azure Functions. So we propose TrainFlow, a distributed training framework designed with serverless paradigm and the performance fluctuation of training in cloud adaptively with programming support. Now, I will go into more detail about the TrainFlow design. Here is the architecture of TrainFlow, consists of the user interface layer, the workflow layer, and the runtime layer. The interface layer for user to submit a training task with training model definition and configuration. Also, user can submit an extension with a tab. The workflow layer maintains the training program. It will be introduced in detail later. The runtime layer to provide higher level states APIs to real states backend. In this part, I will introduce the design of serverless process model in detail. To simplify the design of TrainFlow, a larger serverless process model is adopted. It refers to concept of process in operating systems. So similarly, the serverless process can create children processes and access the context of parent process. Second, a process context to deliver all shared states in the process. A shared state has four types, such as transitive, integer, actor, and external. Transitive states such as ID and graduate is an integer state. Model parameters is an actor state, and such as train argues is external state. Third, identify each function with process ID and function name. Then function can communicate with each other. Okay, based on the serverless process model, we define the TrainFlow process. It consists of task manage process and work process. The task manage process acts as the main process and supports work process. Is for create train task list, controls the epoch and step loops in training. The work process acts as children process. The work process is for feeder tasker, loss model, calculator graduates. We support PS, read or reduce, scatter reduce, 3 training patterns. Now, I will go to introduce how TrainFlow supports programmability extension with event-driven hook. Now, first, user can upload self-defined extensions. It's a tab, including entry, function, events, action. Then register a hook function. When hook function be invoked, will report a new event into event queue. Then the trigger will consume the event to invoke the action. The TrainFlow then generates a new workflow. For better understanding, we show two use cases. When it detects a large fluctuation of synchronization time, the TrainFlow can adaptive selection of training patterns that lead to lower synchronization frequency, such as from BSP to SSP to ASP. When it detects network congestion, the tree flow can adaptive selection of synchronization strategy to reduce communication overhead, such as from synchronized SGD to ADP SGD. In this part, we demonstrate the availability and programmability of tree flow. The experiments are evaluated with 3 ML models, including ResNet 15, DeepFM, and NET. The baseline is Elixir-DL, a Kubernetes-based deep learning framework built on TensorFlow. We can see TreeFlow shows great scalability in all cases. With increase of work number, the performance of TreeFlow is explicitly improved, and the memory consuming of workers in TreeFlow decreases sometimes. For programmability, we consider the two cases discussed above. It is measured with ResNet 15. The result can be viewed from two aspects. First, TreeFlow can effectively support the programming and running of adaptive policies. Second, the adaptive policies can improve the training performance in practice, and the programmability of training framework is worth first promotion. In the end, let us make a conclusion. The motivation of TreeFlow is as managing facilities for distributed ML training is a huge bond for data scientists. It is hard to guarantee distributed training performance with dynamical cloud resources. So to improve the efficiency of distributed ML systems, we propose TreeFlow, a framework for distributed ML training design with serverless paradigm, and support training in cloud adaptively with programming. That's all. Thanks for listening.
Hello everyone, my name is Jie Luo. I come from University of Shanghai for Science and Technology. Now, I'm presenting our paper on DRP, discrete pooling for neural network. The report will be divided into 6 parations. The following I will introduce step by step. Let's start at the research background first. Deep neural networks have achieved great success in computer vision, such as object detection, image classification, and video analysis. However, it's challenging to deploy them in each device, such as mobile phones. The main reason is high computation cost and huge memory footprint. To solve the problem, many approaches of model compression have been proposed, such as spirals, network pooling, quantization, and so on. Because this paper is mainly focused on spirals method and structure pooling, the content of them will be introduced. Spirality is a method by assigning zero values to reduce the number of parameters. Generally, the spirals method judges the importance of width by setting threshold. As shown in the figure, the widths are less than 0.5 will be set to 0. The rest width will be remained. By this way, the parameters of network will be reduced, and the memory footprint will be solved. Pooling is a method by removing redundant parts to compress networks. At present, the mainstream structure pooling are channel pooling and filter pooling. As shown in the figure, redundant filters and corresponding channels are removed entirely. The REST network is still regular and is convenient to deploy them on each device. Now, I want to introduce our proposed pooling algorithm DRP. As shown in the figure, DRP consists of 6 stages. First, we pre-train a neural network and use CBS to spiral string in order to remove unimportant weights in neural network. Then, we extract average rank of feature map and sort them to obtain order rank set. Next, we use DRP to pool and use pre-trained model to fine-tune. Finally, we obtain a pooled model. The inspiration for DRP comes from HiRank. HiRank demonstrates the average rank of feature map generated by a single filter is almost unchanged. Filters with low rank are less important to preserve accuracy, which can be removed first. However, high rank has an issue. The distribution of average rank is very concentrated. Many important filters will be pulled by mistake. As a result, it's necessary to discrete the distribution of average rank. From the formal research, the small wins in the neural network are less contribution to the accuracy of DNNs. It's unwise to extract the rank of feature map directly. So, it's necessary to spiral training. Existing spiral method applying the spiral regulation on the filter width. The training objective function like Formula 1. Lambda and beta are independent on the filter width. Lambda is the scaling factor to indicate the importance of width. Beta is the shifting factor to affect the activation of this convolution layer. Existing spiral method set beta to 0 directly. It's improper. For example, some small widths are set to 0 according to lambda. However, shifting factor beta is very big. It's unwise to set this width to 0, because the activation of this layer are not 0 and still affect the next layer. To remove this issue, Formula 1 is improved as Formula 2. Theta 1 and theta 2 are two different thresholds. Theta 1 is used to determine whether a weight is important. Theta 2 is used to determine whether a bias is important. When a weight is unimportant and the corresponding bias is unimportant, they can be set to 0. This is the principle of CBS. The following I will introduce the experiments and evaluation of DRP and CBS. In terms of data size, we use MNIST CIFAR 10 and CIFAR 100. In terms of networks, we use LearnNet 5, VGNet 16, ResNet 15.6, Google LearnNet, and DeathNet 14. Table 1 shows the accuracy of spiral model with different theta 2. From it, theta 2 can be determined as 0.06. Figure 2 shows the accuracy of spiral models with different theta 1. From it, we can observe that the accuracy of CBS is higher than the accuracy of formal spiral model. and the best theta 1 of LeNet 5 can be determined as 0.03. The best theta 1 of VGNet 16 can be determined as 0.05. Table 2 shows the result of different network models on CIFAR 10. To demonstrate the superiority of DRP, the existing pooling algorithms, such as PFEC, Wilson NP, and HighRank, are used to compare. From table, we can observe that DRP can remove more parameters and flops than other methods on VGNet 16. Moreover, DRP can achieve satisfied results on ResNet 15.6, Google LearnNet, and DeathNet 14. Figure 3 shows the distribution of feature maps' average rank before and after CBS training. The blue dots represent the original rank. The red dots represent the discrete rank. From the figure, we can observe that the distribution of blue dots are very clustering. If we don't conduct CBS on feature maps, many important filters will be pruned by mistake. With the increase of pooling ratio, the accuracy of the model will decrease. From the figure 4, we can observe when the pooling ratio is less than 18%, the accuracy stabilizes around baseline. When the pooling ratio is set around 85%, the accuracy begins to drop. If the pooling ratio is more than 19%, the model will lose the ability to perform image classification. Moreover, from the figure we can observe that the performance of DRP is over HighRank and DRP using spirals. To demonstrate the flexibility of DRP, we also conduct experiments on CIFAR 100 with different networks. The results are shown in Table 3. From it, we can verify DRP is also effective on CIFAR 100. Last, we summarize the main contribution of our work. First, we verify that the average rank of feature maps will distribute more discretely after spiral T training. Based on this, we propose DRP to conduct filter pooling on DNNs. It is convenient to deploy large-scale models on edge device. Second, we analyzed existing spirals method and found that it is necessary to consider the influence of bias term. Based on this, we proposed a neural spirals method named CBS. Second, the outstanding experimental results on different networks and datasets show the flexibility and extendability of CBS and DRP. Thanks for your listening. If you have any question, you can email me.
Hello everyone, my name is Jianan Li. I will present Transmigrator, its transformer-based predictive page migration mechanism for heterogeneous memory. I'd like to give our work's background first. This picture is from Micron's presentation in the middle of the year. Just like its title says, nowadays the data center is more like a memory center. This is the result of the increasing workload, which is data-intensive, like artificial intelligence. They try to build a new highway for heterogeneous memory and storage hierarchy, a kind of physical infrastructure. However, our work tried to give a solution to to use this heterogeneous memory as a logical layer. So why use heterogeneous memory? Because no single type of memory is perfect that will handle all the situations. For example, DRAM and NVM, short for non-volatile RAM. DRAM has smaller capacity compared with NVM, but it has lower latency than NVM. NVM has lower static power, but DRAM has lower dynamic power. Static power is the power when they are idle, and dynamic power is the power of their read and write. So combine them into heterogeneous memory to utilize their both strengths. But the benefit is not out of the box. Its complexity brings new challenges like page management. Page management is crucial to memory system, especially to heterogeneous memory. There are two kinds of organization of heterogeneous memory, vertical and horizontal. In the vertical organization, DRAM is the cache of NVM. In the horizontal organization, DRAM and NVM are combined into one memory space, and they are both addressable. So the core problem of the page management is to decide where to place a given page. A page may move between different memory. So page migration is the important part of the page management.
We reviewed the previous page migration policies and divide them into three categories. First category is based on the read and write beats. Clock DWF use a write beat to manage pages. AC clock use both read and write beats. These approaches are cheap and rough. However, some of them perform well in our experiments. The second category is based on threshold of read and write. TH migrator use fixed threshold to distinguish hot and cold page, but it's hard for this method to achieve a good generalization. For the dynamic threshold, they may lock themselves due to the drastic change. This is the phenomenon we found in our exploration. We need to apply some limitations on the threshold, which turns out to be another hard work. The third category is based on deep learning. Deep Swiper use a LSTM encoder and decoder to predict page numbers. However, their approach shows numeric unstable in our exploration. Another mode, Clio, tries to train a LSTM network for every important page, and they also managed to filter out unimportant pages. Their approach is too complex for us and hard to reproduce. We believe there has got to be a better way. Here we give our solutions for previous problems. In order to get good generalization, we adopt neural networks as well. Instead of training multiple networks as Clio, we use a single network. During the experiment, we found that modeling the task as a regression task will cause the numeric instability, so we choose to model a classification task to eliminate this kind of instability. Also, the classification naturally leads to an end-to-end design, which is what neural networks is good at. Besides, the size of the network is also crucial, because we are in the low system level. We want our network could be as small as possible. This is the overview of our design. The left part is a predictor, which predicts hot pages. We define hot page as the page that will be accessed most in the near future. The right part is a migrator. It tracks page's location and is responsible for migrate hot page to DRAM. It also will do some other things, which will be talked about later. Let's look at the prediction part. The network uses transformer as backbone. We treat page number as words like natural language processing. However, Page numbers are too many to fit into one dictionary, so we divide the page number into small tokens in the same bits, padding their rows into high bits if necessary. Embeddings and query vectors are random initialized and trained with other parameters. The output token will be assembled back into a page number. Labels are derived from the memory trace we collected. We will talk about that later. We also use a threshold method along with the predictor. There are two reasons for this. The first is that the network's accuracy is not high enough to support the whole task alone. We intended to limit its size because size is crucial, and we didn't expect its accuracy could be very high in the very beginning. The second reason is that, although the network performs well in most benchmarks, the accuracy is still relatively low on some benchmarks. So we use two parts together to make the system robust. And one more thing, these two parts will work in parallel. Now let's look at the migration part. It consists of one buffer and three lists. The access buffer is used to store page numbers as the network input. DRAM and NVM have their own list to track their pages. There is also an additional list for candidate page, which is the right square in the diagram. It's used to track the pages that might be hot. It's also the bridge of the predictor and the migrator. We now briefly go through the two data flows in the diagram, distinguished by red and green arrows. The red part belongs to the predictor. The pages in the buffer are fed into the network. The output page will be added to the candidate list. It's unnecessary to synchronize the predictor and the migrator. The predictor can add its output to the list at any time. Of course, the synchronization of operations on that list is still need to be considered. The green path is the data flow of migrator. When a page access occurs, it will first check the DRAM list, then the candidate list, and finally the NVM list. Only one main migration will be performed every page access. In other words, only one of the three green arrows in the box will occur. We say main migration because there might be some other page migrations if some lists are full. Pages in the candidate list will be migrated to DRAM when they are accessed again. These pages also have lifetimes. For example, a page from predictor has the lifetime whose value equals the length of the input sequence. At the end of the cycle, pages exceed their lifetimes will be removed from the candidate list. Some positive false will be filtered out in this way. We apply the fixed threshold to the pages in NVM. If a page in NVM has already been accessed for certain times, it will also be added to the candidate list. Besides, we also adopt redundant copy, dirty bits, and LRU replace policy. Interested readers can find all the details in our paper. Then we give a brief discuss on the overhead of the network. Firstly, the network affects the system more by its prediction results than its inference speed. Without the predictor, the migrator also works, but in low performance. Secondly, multiple access only trigger one inference, so the inference time is relatively loose from this perspective. Our view is that calculation has to be done, but delay might be hidden. We evaluate our design with memory trace collected by ourselves. We use SPEC CPU 2006 as benchmarks and use Gem5 simulator to simulate the 3-level cache. The table shows our simulation configuration of Gem5. There are data cache and instruction cache, which are both 32 kilobyte, and a 1512 kilobyte level 2 cache. These three caches are both 8-way side associative. The L3 cache is 4 megabyte. All the caches above have 64-byte cache line. We run 100 million instructions for each benchmark. We train our network with these memory traces. The network is small. Its encoder and decoder only have 2 layers, and the model dimension is 64. The total parameter size is 0.8 megabyte. Considering its size, 72% accuracy is quite satisfying for us. We use 32-bit address space and choose token length to be 8 bits in the end. Big token size will increase the dictionary size and make the loss high, the accuracy low. Small token size will reduce the loss, but the accuracy is still low. In the end, we found 8 bits is the best length. We wrote a cycle simulator to evaluate our design. We compared our design with AC clock, TH migrator, and VCHMM. Page migration latency are technically ignored. Otherwise, the optimal will always be placing all the page in NVM. The table shows the simulation parameters, all from previous works. Our method achieved low access latency. The access latency is very important index to memory system. The blue bar is our method. The shadow part is the access time of NVM, and the rest part is the access time of DRAM. From this chart, we can see that other methods will perform not well in some situations, but our methods are robust in all benchmarks. It's worth to notice that the method based on dynamic threshold, which is the red bar, will have very high latency in some benchmarks. During the debugging, we found that its threshold become very large, so that almost no page will be migrated from NVM to DRAM. We call it self-lock. Our method achieved reasonable migration count. Unlike access latency, we want latency as low as possible, but the migration count should not be too few. For example, the fixed threshold method, which is the green bar, has less migration than other methods, but it also leaves lots of hot page in NVM, which undermines the performance. Our method also achieved reasonable energy consumption. Migration latency might be hidden, but the energy cost cannot. This chart almost have the same shape of the previous one. The more migrations, the more energy will be used, because we use 4 kilobyte page size, which is quite large compared with the cache line. There are many areas where we can improve our work. For example, we can distinguish read and write in the labels, which might be an better optimal for the neural network. We also can explore other page migration policies in the migration part. In conclusion, we designed an end-to-end page predictor based on deep learning. We proposed Transmigrator, a framework that combines traditional page migration methods with deep learning one. Our design reduced access latency by 23% on average over other methods, and kept almost the same migration count and energy consumption. Thank you for your listening.
Hello everyone. I'm delighted to be here and have this opportunity to share something with you. Today, I will introduce our work in hardware acceleration for one-dimensional convolutional neural network-based real-time edge computing. Nowadays, with the dramatic growth in deep learning, the demand of computing resources has greatly increased. Nevertheless, the imminent end of Moore's law makes it challenged on continuing scaling conventional computer architectures and satisfy the various demands. These two reasons jointly push toward the development of domain-specific architecture. One-dimensional convolutional neural network has become a widely used deep learning algorithm. The structure of one-dimensional convolution makes 1D CNN usually apply in time series classification, such as acoustic recognition, EEG recognition, and signal peak detection. These applications of 1D CNN are usually deployed at edge and generally rely on pattern recognitions on most recently collected samples, which cause limited timing constraint to process the data before the new data is collected, posing a real-time requirement. In conventional scenario, all the inference data is already stored in storage device. During the computation phase, any element in the feature map is accessible. Therefore, the accelerator can perform accelerated optimization for the completely feature map. But in RTC scenario, the sampling device continuously samples data and streams stored in storage device. The accelerator can only optimize the incomplete feature map of inference because of the streaming data. Specifically, the sampling device streaming the data in an element-wise manner and recursively constructed the inference feature map in storage device. In fact, the real timing requires that the accelerator need to complete the computation of the latest element before a new element is streamed. Moreover, in order to prevent important features from being miscovered in the boundary part, the successive input feature map usually have a large intersection. This will cause a lot of repeated computations in the inference process, thereby increasing the hardware resources. We propose a scheme of data reuse to maximally reduce the computational and memory resources, and design a hardware accelerator architecture to quickly respond for the latest input data. Firstly, let's focus on the scheme of data reuse. We hereby give an example of one-dimensional CNN to show the operating process better. The CNN have two convolutional layers and one pooling layer. The specific configuration is shown in the left table. This network takes an input of size 19 and gives an output of size 4 at the end. As mentioned above, the successive input feature map in RTC system have a large intersection. In this example, we give 5 successive input feature maps with the size of 19. Each 2 successive input feature map only have one element difference. The figure shows the specific intersection between the first and the second feature map. Based on these input feature maps, the figure after showed the process through the 1D CNN. For the result of first convolutional layer, it can be seen that the result of these 2 successive input feature map of this layer with stride is1 is also have large intersection. Therefore, the result of second feature map in this layer can be constructed by partial result of the first feature map and the convolutional result of the element different from the first feature map. Let's continue to focus on the result of the next pooling layer. In this layer, with the stride is2, the result of the first and the second feature map have no any intersection. But the result of the first and the third feature map in this layer have a large intersection, which means that the result of third feature map can also be constructed by partial result of the first feature map and the result of the element difference from the first feature map through one convolutional layer and one pooling layer. It can be noticed that the difference of the index of these 2 feature maps is equal to the product of the stride in all layers. For the second convolutional layer, only the result of the first and fifth feature map have intersection in this layer, and the result of fifth feature map can be constructed by the intersection part in result of the first feature map and the result related to latest data in fifth feature map. Meanwhile, the product of the stride in all layer is 4, which is also equals to the difference of the index of these 2 feature maps. According to the phenomena observed above, we can draw the following conclusions. For any feature map, except for last element of the result in the ith convolutional or pooling layer, other elements have been computed in the previous feature map operating process at different time, and the last element is computed by the latest several elements in previous layer. which are also have been computed in the previous feature map operating process. Therefore, the scheme we propose is to take out the intermediate result that have been computed at the previous time point, instead of repeated computation when computing the last element in a kernel. And this figure shows the basic relation on intersections and reuse data in different layers. Based on the data reuse scheme, we provided structures of the typical layer. The figure shows the convolutional layer. The processing element in this layer is used for multiplication of one element and corresponding weight, and accumulating the result of previous processing element. A processing block is constructed by multiple processing elements. Each processing block completes the computation of one input channel of the convolutional kernel. The data participating in computation in processing block is stored in input register and reuse register separately. The input data register only stores the last element in the kernel, which is complete computed in previous layer. The reuse data register stores the reusable data product during previous computations. The final results can be accumulated by multiple cycles, so the number of processing blocks can flexibly adjusted according to the requirements. The result of this mode will be immediately processed by next layer and also will be reused for future computations. This figure shows the pooling layer and the fully connected layer. The pooling layer also have input register and reuse data registers. The last element of one pooling kernel is stored in input register. Other elements will be fetched into the reuse data register. Like the convolutional layer, the pooling result is both processed by the next layer and stored in for future computations. The structure of a fully connected layer is also mainly composed of processing blocks. Each processing block forms a neuron. The number of processing elements used in a processing block is adjustable from 1 to the number of inputs of a neuron. For a fully connected layer, we change both the number of processing blocks and the number of processing elements in a processing block to meet the design-specific and balanced latency of each layer. We provide the overall architecture in pipeline design. In this design, all layers are connected with the RAM. All registers within a layer are controlled by an interlayer clock, and the convolutional and fully connected layers operate in a two-stage pipeline and fetch and compute. By properly adjusting the number of processing blocks and processing elements in each layer, it is possible to ensure that each convolutional or fully connected layer completes the computation in a similar number of cycles. Thus, we set interlayer clock to control these cycles, and use interlayer register to save the complete result of previous layer connected before the register. On the other hand, we design a compiler for one-dimensional CNN architecture generation. Firstly, we obtain its relevant configurations for the PyTorch implementation of a certain one-dimensional CNN, such as layers, kernel size, and stride. Then we separately struct the typical layer by chisel, and leave their configurations determined by the applied network structure. Meanwhile, we generate the weight and bias from a training process in Python. The network structure in Chisel is then compiled to synthesizable behavior model in Verilog. Finally, we exploit the Synopsys design compiler to produce and evaluate the structure model. To evaluate our proposed architecture, we quantize 1D CNNs to 8-bit fixed point precision and implement them by TSMC 65 nanometer CMOS technology. These designs are synthesized by the design compiler, and we perform static timing and power analysis of design compiler to measure the clock frequency and power consumption. The network structure involved in our evaluation are based on the audio processing subnet of SoundNet with an additionally fully connected layer. We use several datasets for UEA datasets to train the utilized network and make some adjustment of network architecture for every dataset. The right table shows the specific configuration of each dataset. For the structure demonstrated in previous table, we utilize the compiler to generate all possible implementations supporting different numbers of MACs, and we show their power latency and bandwidth in this graph. As the number of MACs increase, power consumption and bandwidth also naturally proportional increase. In each case, the power consumption is relatively low and the required bandwidth is achievable. The latency here represents time that from a complete input feature map is available until the classification result is produced. It can be noticed that the latency is dramatically reduced if more processing blocks are included in a design. The reason is that more processing blocks are allocated makes convolutional or fully connected layer possible to compute more data in one cycle, thus reduce the overall latency. Furthermore, comparing the network with different number of layers, the overall latency largely increases for a network with more layers. This is because the number of input channels exponentially increases for a deeper layer, and thus more clock cycles are required to produce the result. However, even for the case of eigenworms, the latency can be reduced up to 36.12 microseconds. We compared the proposed architecture with 7-layer user eigenworms classification with existing works in this table. Our proposed architecture operates at a frequency of 62.5 MHz, which is lower than some existing works in table. The power consumption of our design is in the range of 17.49 to 62.56 mW, generally lower than the existing works. The power efficiency of our work is in the range of 0.72 to 1.72 TOPS per watt, depending on the total number of max supported by a design. Finally, the latency is hugely reduced to the range of 36.12 to 4,587.8 microseconds from a few milliseconds for some existing works. However, as the compared designs are developed based on different networks, we further compute latency per layer to reveal the efficiency of our architecture. It can be noticed that the latency per layer of our architecture is from 5.16 to 655.4 microseconds. Compared with the DAC19 and DTCNN, the maximum latency per layer is compatible with those works. While it notes that minimal latency per layer can be reduced for more than one order in magnitude with the power efficiency close to those works. This is because the proposed architecture initiates computations simultaneously when the input feature map is streamed, so that it does not rely on the availability of complete input feature map to initiate the CNN operations. In conclusion, we propose a one-dimensional CNN accelerator for edge inference of RTC system. We propose to perform element-wise computations to realize an immediate execution for the currently available input data due to the non-current availability of the input feature map. A scheme of data reuse proposed to maximally reduce the computations and memory resources based on the generation of one-dimensional CNN feature maps during RTC system. The accelerator is constructed in pipeline architecture through a development compiler for any one-dimensional CNN models. We implement our proposed architecture by a 69 nanometer technology and show its maximal power efficiency as 1.72 TOPS per watt. Finally, we show our design can outperform state-of-the-art CNN accelerators with a reduction of more than one order to magnitude in terms of latency. That is all what I want to share today. Thank you for your attention.
Concluded our morning talk. In the morning session, we have covered exciting papers in computer architecture as well as in deep learning. I hope you guys have a very nice lunch break. We convene at 2 p.m. to hear exciting talks regarding storage and I/O, cloud computing, as well as emerging applications. So have a nice break. I will see you in the afternoon. Thank you very much.